What if everything you see around you, from the stars in the night sky to the ground beneath your feet, is just the surface of a much deeper, hidden reality? We often look out at the universe and see planets, galaxies, and vast expanses of empty space, believing we understand the rules of the cosmic game. But what if the true architects of reality are forces we cannot see, influences that work in the shadows, weaving the very fabric of existence itself with invisible hands? It's a staggering thought that our entire cosmos, with all its breathtaking beauty and terrifying power, is being shaped, molded, and guided by energies and principles that remain just beyond our direct perception. This isn't about ghosts or supernatural myths. This is about the fundamental and often bizarre mechanics of the universe that science is only just beginning to unravel. These are the unseen cosmic forces, the hidden players in the grand theater of reality, and they hold the keys to understanding not just where we came from, but the ultimate fate of everything. Today, we're embarking on a journey to pull back that cosmic curtain. We will explore 30 of these profound and mysterious forces, diving into a world where the familiar laws of physics twist into strange new shapes, where empty space seethes with potential, and where the very concept of what is real gets challenged at the most fundamental level. This is not a simple list of facts. It is an expedition into the heart of cosmic mystery. We will venture from the mind-bending implications of dark energy, which is relentlessly tearing the universe apart, to the enigmatic pull of dark matter, an invisible scaffolding that holds galaxies together. We will confront the bizarre rules of quantum mechanics, where particles can be in two places at once and communicate instantaneously across vast distances. We will even question the nature of time itself, and whether our linear experience of past, present, and future is merely an illusion. Each force we uncover is a piece of a grander puzzle, a step closer to seeing the universe not as a collection of separate objects, but as a single, interconnected whole humming with unseen activity. This voyage is about more than just satisfying scientific curiosity. It's about connecting with the profound wonder of our existence. By understanding these hidden forces, we begin to see our own place in the cosmos in a completely new light. We are not just passive observers living on a tiny rock in a random solar system. We are active participants in a dynamic, evolving universe, our very lives touched by these invisible currents. So get comfortable, open your mind, and prepare to have your perception of reality forever altered. What follows is a deep and thoughtful exploration of the 30 unseen cosmic forces that shape reality, a journey to the very edges of our understanding and beyond, into the magnificent and mysterious depths of the cosmos. Let's begin. Our journey into the unseen begins with the most famous cosmic ghost of them all, dark matter. Think about the last time you saw a picture of a majestic spiral galaxy, its arms swirling in a cosmic dance. Now imagine that everything you can see in that image, every star, every nebula, every speck of cosmic dust, is only a tiny fraction of what's actually there. The rest, the overwhelming majority of the galaxy's substance, is completely invisible. This is the profound and humbling mystery of dark matter. It is a form of matter that does not emit, absorb, or reflect any light, making it utterly transparent across the entire electromagnetic spectrum. We cannot see it with any telescope, no matter how powerful, and yet we know it must be there because of its immense gravitational pull. It is the universe's ultimate phantom, felt but not seen, and it makes up roughly 27% of the entire cosmos. How did we ever discover something we cannot see? The first major clue came from the way galaxies spin. According to the laws of gravity as defined by Newton and Einstein, stars on the outer edges of a spinning galaxy should move much more slowly than those near the dense center, just as the outer planets in our solar system orbit the sun more slowly than the inner ones. But when astronomers actually measured the rotational speeds of galaxies, they found something astonishing. stars on the galactic outskirts were moving just as fast as those near the core. It was as if the entire galaxy was spinning as a single, solid plate. The only plausible explanation was that each galaxy was embedded within a massive, invisible sphere of matter, a dark matter halo, whose immense gravity was pulling on the outer stars, whipping them around at speeds that should otherwise send them flying off into intergalactic space. Another brilliant piece of evidence comes from a phenomenon known as gravitational lensing. Einstein's theory of general relativity tells us that massive objects warp the very fabric of space-time, and light traveling through this warped space will bend its path. When we look at a massive object like a galaxy cluster in the distant universe, its tremendous gravity, dominated by dark matter, acts like a giant cosmic lens. It bends and distorts the light from even more distant galaxies behind it, creating stretched, magnified, and sometimes even multiple images of those background objects. By studying the pattern of this distortion, astronomers can literally map the distribution of the invisible mass causing it. The resulting maps reveal vast, intricate webs of dark matter, a hidden skeleton upon which the visible universe is built. This phantom architecture holds entire clusters of galaxies together, preventing them from tearing themselves apart under the strain of their own motion. So, what is this mysterious substance that remains one of the greatest open questions in all of physics? We know what it is not. It is not the same as the black holes or dark clouds of normal matter we already understand. The leading hypothesis points to entirely new kinds of fundamental particles, exotic relics from the universe's first moments that interact with ordinary matter almost exclusively through gravity. Countless experiments deep underground, shielded from cosmic rays, are searching for the impossibly rare collision between a dark matter particle and an atom in a detector. So far, they have found nothing definitive. This persistent elusiveness only deepens the enigma. Dark matter is the silent partner in the cosmic dance, the unseen hand that sculpts the grandest structures in the universe, and our first humbling clue that the reality we perceive is only a sliver of what truly exists. As we grapple with the ghostly presence of dark matter holding the cosmos together, we encounter an even more formidable and counterintuitive force working on the grandest scale imaginable: dark energy. If dark matter is the universe's invisible glue, then dark energy is its mysterious anti-gravity, a repulsive force causing the very fabric of space itself to stretch apart at an ever-increasing rate. This discovery, which earned the Nobel Prize in Physics in 2011, completely overturned the long-held assumption that the universe's expansion, following the Big Bang, should be slowing down over time due to the collective gravitational pull of all the matter within it. Instead, astronomers found the cosmos is not just expanding, it's accelerating, as if every galaxy is being pushed away from every other by some unseen, pervasive energy woven into the vacuum of space. The evidence for this staggering acceleration came from observations of distant stellar explosions known as Type 1, a supernova. These cosmic beacons are considered standard candles because they explode with a known, predictable brightness. By measuring how dim they appear from Earth, astronomers can calculate their distance with remarkable accuracy. Furthermore, by analyzing the redshift of their light, how much its wavelength has been stretched as the universe expands, scientists can determine how fast the universe was expanding when that light was emitted billions of years ago. When two independent teams painstakingly compared these distances and redshifts in the late 1990s, they expected to confirm the cosmic slowdown. To their profound astonishment, the data revealed the opposite. The expansion of the universe was speeding up. The most straightforward explanation for this relentless push was the existence of a previously unknown form of energy, a dark energy, comprising a staggering 68% of the universe's total energy budget. So, what could this energy be? The leading candidate is something Einstein himself proposed: then later discarded as his greatest blunder, the cosmological constant. This concept represents a constant energy density that is an inherent property of the vacuum of space itself. Think of empty space not as a true nothingness, but as a seething, bubbling quantum foam where virtual particles flicker in and out of existence. This underlying activity could generate a kind of negative pressure, causing empty space to repel itself. In this view, dark energy isn't a force that acts in space, but rather a property of space. As the universe expands and more space comes into existence, the total amount of this repulsive energy increases, leading to a runaway acceleration that will continue forever. However, the cosmological constant is far from the only idea on the table. Some theoretical physicists propose that dark energy is not constant at all, but a dynamic field that has changed over the lifetime of the cosmos, and concept sometimes referred to as quintessence, a throwback to the ancient Aristotelian idea of a fifth element. Others entertain the possibility that our understanding of gravity itself is incomplete on cosmic scales, and that Einstein's theory of general relativity, while exquisitely accurate in our solar system, needs modification to explain the behavior of the entire universe. These debates are not merely academic, they strike at the heart of our comprehension of fundamental physics and the ultimate fate of the cosmos. A constant dark energy suggests a future where the universe expands forever into a cold, dark, and lonely emptiness, while a dynamic one could lead to a variety of other fates, including a potential big rip where the fabric of spacetime itself is torn apart. This invisible force, completely dominant in our current epoch, is quietly writing the final chapter of the universe's story, and we are only just beginning to decipher its opening lines. While dark energy pushes the cosmos apart on the grandest stage, there is another, equally profound force operating at the very smallest scales. A force so fundamental that it underpins the very existence of everything, including dark energy itself. To find it, we have to venture into the seeming emptiness of space. When you look up at the night sky, the void between stars appears utterly black and still. But this perception of true emptiness is a grand illusion. According to the bizarre rules of quantum mechanics, the vacuum of space is not a placid, quiet nothing. Instead, it is a seething, turbulent ocean of energy constantly in motion. At scales a trillion times smaller than an atom, the very concept of nothing breaks down entirely. This is the domain of quantum fluctuations, temporary and spontaneous changes in energy that defy our everyday intuition. The core principle here is Heisenberg's uncertainty principle, a cornerstone of quantum theory. This principle tells us that there is a fundamental limit to how precisely we can know certain pairs of properties of a particle. One of the most consequential pairings is energy and time. It states that for an incredibly brief moment, the energy within a region of space can fluctuate wildly, as long as it averages out to zero over a longer period. In practice, this means that empty space is never truly empty. It is a dynamic arena where packets of energy continuously pop into and out of existence. These fleeting bursts of energy often manifest as pairs of virtual particles, a particle and its antimatter counterpart, like an electron and a positron. They spontaneously appear together, exist for a fleeting instant, and then annihilate each other, returning their borrowed energy back to the vacuum. This isn't just a theoretical idea, we have direct experimental evidence for it. The Casimir effect, for instance, demonstrates this beautifully. When two uncharged metal plates are placed extremely close together in a vacuum, they are pushed toward each other by a faint, measurable force. Why? Because the tiny space between the plates restricts the kinds of quantum fluctuations that can occur, while the vast space outside the plates allows for a greater variety. The result is a pressure differential, more virtual particles pushing from the outside than from the inside. That drives the plates together, providing a tangible signature of this ghostly quantum activity. The significance of these fluctuations extends far beyond a curious laboratory effect. They are the very seeds from which our entire universe may have grown. In the theory of cosmic inflation, the universe underwent a period of exponentially rapid expansion in the first fraction of a second after the Big Bang. During this incredible growth spurt, the microscopic quantum fluctuations that permeated the primordial universe were stretched to astronomical sizes. The tiny, random variations in energy density became the blueprints for the large-scale structure of the cosmos. The slightly denser regions, where fluctuations had concentrated a little more energy, became the gravitational seeds that eventually collapsed under their own weight to form galaxies, clusters, and superclusters. This means that the majestic cosmic web we see today, the vast filaments of galaxies surrounding immense voids, can be traced back directly to these unpredictable subatomic tremors in the fabric of spacetime. We are, in a very real sense, living in the amplified echo of quantum noise from the dawn of time. This idea is powerfully supported by the cosmic microwave background radiation, the afterglow of the Big Bang. This faint radiation bath fills the entire sky, and when we map its temperature with exquisite precision, we find it is not perfectly uniform. Instead, it contains tiny, mottled variations, hot and cold spots that differ in temperature by only a few millionths of a degree. These minuscule imperfections are a frozen snapshot of the density fluctuations that existed when the universe was just 380,000 years old, and they match the pattern predicted by the stretching of primordial quantum fluctuations during inflation. It is a staggering connection. The largest observable structure in the universe bears the indelible fingerprint of the smallest possible physics. Quantum fluctuations are not merely a curious sideshow. They are the original architects, the random but essential scribbles that dictated where galaxies would one day bloom and where vast cosmic deserts would remain. Without this fundamental, seething activity in the void, our universe would be a featureless, sterile expanse, and we would not be here to ponder its origins. But if quantum fluctuations are the architects of cosmic structure, what gives those structures their substance and weight? What stops the fundamental building blocks of matter from simply racing across the universe at the speed of light, never cohering into the atoms that form planets, people, and stars? The answer lies in a different kind of field, one that is arguably even more fundamental to our existence. This is the Higgs field, an invisible energy field that permeates every cubic inch of the universe, from the emptiest void to the heart of our own planet. Unlike the gravitational or electromagnetic fields, which vary in strength, the Higgs field is thought to have a constant, non-zero value everywhere. Its sole cosmic purpose is to interact with other particles, and in doing so, it bestows upon them the property we know as mass. To understand how this works, picture the universe as a vast, endless party, and the Higgs field is like a crowd of people uniformly filling the room. Now imagine different guests trying to move through this crowd. A photon, the particle of light, is like a famous celebrity that nobody recognizes. It doesn't interact with the crowd at all. It zips through the room completely unimpeded, moving at the ultimate speed limit of the cosmos. This is why light has no mass. An electron, on the other hand, is a somewhat well-known figure. It might get a few glances and a handshake or two as it moves, slowing it down a bit. It has a small amount of mass, and then there's a top quark, one of the heaviest fundamental particles. This guest is a major celebrity. The moment it enters the room, it is mobbed by the crowd. It can barely move. It has to push and struggle just to take a single step. Its movement is severely hindered, and this immense difficulty in moving through the Higgs field crowd is what we experience as a very large mass. This interaction, this drag on particles as they move through the ubiquitous Higgs field, is the Higgs mechanism. It's not that particles are inherently heavy in the way we think of a rock being heavy. Rather, their mass is a measure of how strongly they interact with this all-pervading cosmic molasses. For decades, the Higgs field was a brilliant but unproven piece of the standard model of particle physics, the theoretical framework that describes the fundamental particles and forces. The theory was beautiful and powerful, but it had a glaring hole without this mechanism. The problem was you can't directly observe a field. You can, however, observe its signature. Just as you can prove a distant pond exists by throwing a stone and seeing the ripples, physicists knew they could confirm the existence of the Higgs field by creating a ripple within it. That ripple is what we call the Higgs boson. This particle is not the field itself, but a tiny, localized excitation of it, a proof of its existence. Finding this particle became one of the greatest scientific quests of our time, leading to the construction of the most complex machine ever built, the Large Hadron Collider at CERN. Buried deep underground beneath the border between Switzerland and France, the Large Hadron Collider is a 17-mile ring where protons are accelerated to within a whisper of the speed of light and then smashed together head-on. These collisions recreate, for a fleeting instant, the conditions of the universe a trillionth of a second after the Big Bang, birthing a fireball of energy from which new, exotic particles can momentarily spring into existence. For years, the giant detectors known as ATLAS and CMS sifted through the debris of trillions upon trillions of these collisions, looking for a specific telltale signature among the chaos, a pattern of decay products that could only have come from the brief creation and subsequent disintegration of a Higgs boson. The task was astronomically difficult, like finding one specific grain of sand on all the beaches of the world. Then, on the 4th of July 2012, the scientific world held its breath as the directors of the two experiments announced their results. The data showed a clear, unambiguous bump in their data, a signal. They had found it. The Higgs boson was real. This monumental discovery was more than just the completion of a checklist. It was a profound validation of our understanding of the universe at its most fundamental level. It confirmed that the Higgs field is real, that this invisible cosmic treacle truly does fill the void, and that it is responsible for imparting mass to the elementary particles. Without it, electrons would have no mass and atoms could not form. There would be no chemistry, no planets, no life. The universe would be a soup of massless particles forever racing through an empty darkness. The Higgs field is thus a silent, passive, and universal force that makes our material world possible. It operates in the background of everything, a foundational presence that gives substance to reality itself, allowing the quantum seeds from the dawn of time to grow into the rich and complex cosmos we call home. Now, to understand the true power of those quantum seeds, we need to rewind the cosmic clock back to the very beginning, to a concept so radical it reshaped our entire view of the universe's birth: cosmic inflation. Imagine the universe not starting with a slow, stately expansion, but with a sudden, violent, and exponential growth spurt, in the tiniest fraction of a second, from about 10 to the negative 36 seconds to 10 to the negative 32 seconds after the Big Bang. The cosmos is thought to have doubled in size at an incredible rate, not once or twice, but perhaps 100 times or more. In less time than it takes for light to cross a single proton, the entire observable universe inflated from a subatomic speck to something roughly the size of a grapefruit. This wasn't the steady expansion we see today, driven by dark energy. This was a primal, explosive stretching of spacetime itself, triggered by a mysterious repulsive energy field that dominated the infant cosmos. This idea of inflation didn't just come from nowhere. It was proposed to solve some of the most perplexing puzzles in cosmology. The first is known as the horizon problem. If you look at the cosmic microwave background radiation in opposite directions in the sky, the temperature is the same to an astonishing degree of precision, down to about 1 part in 100,000. This is deeply strange. In the standard Big Bang model without inflation, these two regions on the sky would have been too far apart for light or any kind of influence to have traveled between them in the age of the universe. They should never have had a chance to reach the same temperature, just as 2 cups of coffee in different cities can't naturally cool to the exact same temperature without some connection. Cosmic inflation solves this by proposing that these vastly separated regions were, in fact, once in intimate contact in that tiny pre-inflationary speck. The incredible, faster-than-light expansion of space then stretched them far apart, but they retained their thermal equilibrium from that initial connected state, preserving a uniform temperature across the sky. The second major puzzle is the flatness problem. Observations tell us that the overall geometry of our universe is remarkably flat, meaning that parallel lines will never meet and the angles of a triangle add up to exactly 180 degrees. This is a very special, finely tuned condition. Think of the universe's density as being balanced on a knife's edge. If the density were even slightly higher at the beginning, the universe would have quickly collapsed back in a big crunch. If it was slightly lower, it would have expanded so rapidly that galaxies and stars could never have formed. For our universe to be as flat as we observe it to be after nearly 14 billion years, its initial density had to be fine-tuned to an accuracy of 1 part in 10 to the power of 60, an unimaginable precision. Inflation provides a beautiful and natural solution. The rapid stretching of space during that initial epoch acts like a cosmic iron, smoothing out any initial curvature. Just as inflating a small, wrinkled balloon makes its surface appear much larger and flatter, the inflationary expansion drove the geometry of the observable universe toward perfect flatness, regardless of its initial crumpled state. But perhaps the most profound gift of inflation was providing the origin story for the large-scale structure we see today. You'll recall the quantum fluctuations that constantly stir the vacuum of space. During the inflationary period, these microscopic tremors were not left behind. As the universe inflated at a breathtaking rate, these tiny, random quantum fluctuations in the inflationary energy field itself were stretched to macroscopic sizes. Regions of space that had a tiny bit more energy inflated slightly less, while regions with a tiny bit less energy inflated slightly more. This process imprinted a specific pattern of minute density variations: slightly hotter, denser spots and slightly cooler, emptier spots across the entire cosmos. These minuscule imperfections, born from quantum uncertainty, became the gravitational seeds for everything that followed. After inflation ended, the energy driving it decayed, flooding the universe with a hot plasma of particles and radiation, but the blueprint was already set. Over billions of years, gravity amplified those seeds, pulling more matter into the denser regions, which eventually collapsed to form the first stars, galaxies, and the vast cosmic web of filaments and voids. Scientists test this incredible story using sophisticated computer simulations of the early universe. These aren't simple animations, they are complex mathematical models that incorporate the laws of physics, the known properties of dark matter and dark energy, and the initial conditions set by inflation. When researchers run these simulations forward in time, starting with those primordial quantum fluctuations, they watch as gravity works its slow, patient magic. The simulations show a universe evolving from a nearly smooth soup of matter into an intricate, web-like structure that looks astonishingly like the one we observe through our most powerful telescopes. The statistical properties of the galaxy clusters and the voids in these simulated universes match the real data with stunning accuracy. This powerful agreement between theory and observation is one of the strongest pieces of evidence we have that a period of cosmic inflation did in fact occur. It tells us that the grand tapestry of the cosmos, with its billions of galaxies, was woven on a loom of quantum mechanics, its pattern determined in the first fleeting moments of existence by a force of unimaginable power. From the explosive stretching of cosmic inflation, we now turn to the lingering echoes of the most violent events in the modern universe: gravitational waves. Just as a pebble dropped into a still pond sends ripples traveling outward across the water, massive objects in space, when they accelerate, send ripples traveling outward across the very fabric of space-time itself. This was one of the most stunning predictions of Einstein's theory of general relativity. He theorized that gravity isn't just a force that pulls objects together, but rather the result of massive objects warping the four-dimensional continuum of space and time. When those massive objects move, especially when they accelerate dramatically, like two black holes spiraling around each other, they create disturbances in this cosmic fabric. These disturbances propagate outward at the speed of light as waves, literally stretching and compressing space itself as they pass by. For a century, gravitational waves remained a purely theoretical concept, a ghostly signal thought to be so faint that it would be impossible to ever detect on Earth. The challenge was almost unimaginable. A passing gravitational wave from a distant cosmic collision would change the distance between 2 points by an almost infinitesimal amount. We're talking about a change in length far smaller than the diameter of a single proton over a distance of several miles. Catching such a subtle whisper required one of the most sensitive instruments ever constructed, the Laser Interferometer Gravitational Wave Observatory, or LIGO. The LIGO facilities are essentially giant L-shaped vacuum chambers with arms 4 kilometers long. At the heart of each detector is a laser beam that is split and sent down the 2 perpendicular arms, bouncing off exquisitely polished mirrors at the ends and then recombining. In normal circumstances, the light waves cancel each other out, but when a gravitational wave passes through the Earth, it does something remarkable. It stretches space in one direction while simultaneously compressing it in the perpendicular direction. This minuscule distortion changes the length of one arm relative to the other by that tiny proton scale amount. This shift causes the laser light waves to fall out of sync, creating a flicker of light at the detector's output, a signal. On September 14, 2015, after decades of development and refinement, that flicker finally appeared. For the first time in history, humanity had directly detected gravitational waves originating from the collision of 2 black holes over 1.3 billion years ago. The sources of these cosmic tremors are as dramatic as the waves themselves. The most common signals LIGO and its European counterpart, Virgo, have detected come from the final, frantic moments of binary systems, pairs of incredibly dense objects like neutron stars or black holes. As these objects orbit each other, they lose energy by emitting gravitational waves, causing their orbits to slowly decay. They spiral inward over millions of years, getting closer and faster until, in a final cataclysm, they merge into a single, more massive object. The collision of 2 black holes is an event of almost incomprehensible power, converting an amount of mass several times greater than our Sun directly into energy in the form of gravitational waves in a fraction of a second. The signal detected on that historic day in 2015 was the signature of this final inspiral and merger, a characteristic chirp that rose in frequency and amplitude before culminating in a final, ringing bang as the 2 black holes became one. Since that first detection, the observatories have recorded dozens of such events, opening up an entirely new branch of astronomy. This new sense gives us a way to observe the cosmos that is completely different from traditional astronomy. For all of human history, we have studied the universe using light, from visible rays to radio waves and X-rays. But light can be blocked, absorbed, or scattered by dust and gas. Gravitational waves, however, pass through matter almost completely unimpeded. They offer a direct, unadulterated view into the most energetic and dark corners of the universe. They allow us to hear events that are completely invisible to telescopes, like the merger of 2 black holes that emit no light whatsoever. Furthermore, by comparing the arrival times of a wave at multiple detectors across the globe, scientists can triangulate the position of the source on the sky, allowing other telescopes to swing into action and look for any accompanying flash of light or other electromagnetic radiation. This multi-messenger astronomy came of age in 2017 when LIGO and Virgo detected the merger of two neutron stars. Within seconds, observatories around the world and in space were able to pinpoint the source and witness the brilliant kilonova explosion, confirming that such collisions are the cosmic forges where heavy elements like gold and platinum are created. Gravitational waves are not just another tool in the astronomical toolkit. They are a fundamentally new sense, allowing us to listen to the symphony of the universe and perceive the hidden dance of spacetime itself. While gravitational waves allow us to hear the collisions of black holes, another ghostly messenger offers a direct look into the heart of stars themselves, a particle so elusive it can pass through light years of lead without a single interaction. This is the neutrino, and its strange ability to shapeshift as it travels reveals one of the most subtle and profound forces shaping our understanding of particle physics. Born from some of the most violent processes in the cosmos, from the nuclear fires of the Sun to the cataclysmic explosions of supernova, trillions of these particles are streaming through your body every second, completely unnoticed. For decades, scientists believed neutrinos were entirely massless, ghostly spectators that carried energy away from nuclear reactions but interacted with almost nothing. This belief was upended by a simple but baffling observation. We weren't finding as many neutrinos as our theories predicted we should. The mystery began deep underground, in a vast tank of cleaning fluid buried in a South Dakota gold mine. This was the Homestake experiment, designed to catch neutrinos emitted by the Sun. According to our best models of solar fusion, a specific number of these particles should have been arriving at Earth every second. But the detector was only catching about 1/3 of the expected amount. For years, physicists wrestled with this solar neutrino problem, checking and rechecking their models of the Sun and their experimental setups. Was our understanding of stellar fusion wrong, or was something strange happening to the neutrinos on their journey? The answer, when it finally came, was more fantastic than anyone had imagined. The neutrinos weren't missing, they were changing. They were oscillating from one type or flavor to another, effectively disguising themselves from detectors that were only looking for one specific kind. This phenomenon, known as neutrino oscillation, is a direct violation of the original standard model of particle physics, which stated that neutrinos must be massless. Here's why it's so revolutionary. Neutrinos come in 3 flavors, each associated with a different, heavier particle: the electron neutrino, the muon neutrino, and the tau neutrino. Oscillation means that an electron neutrino produced in the Sun's core does not remain an electron neutrino for its entire life. As it travels through the vacuum of space, and even through the Earth, it morphs, quantum mechanically transforming into a muon neutrino, then a tau neutrino, and then back again. This is not just a simple name change, it is a fundamental identity crisis driven by quantum mechanics. For this shapeshifting to be possible, neutrinos must have mass, however tiny. A massless particle, like a photon, travels at the speed of light, and from its perspective, time does not pass. For it, the journey from the Sun to the Earth is instantaneous. But if a particle has even an infinitesimal amount of mass, it travels at a speed slightly less than light, and time passes for it. This passage of time is essential for the oscillation to occur. It's the internal quantum clock of the neutrino that allows its identity to evolve and change during its flight. The implications of this discovery are staggering. First, it forces us to revise the standard model, our most successful theory of the fundamental particles and forces. For decades, the model was a perfect, self-consistent puzzle, and the confirmed masslessness of the neutrino was a key piece. Now that we know neutrinos have mass, however slight, it is clear the model is incomplete. It points toward new physics, perhaps involving a deeper connection between particles or the existence of a new, even more elusive type of neutrino, the so-called sterile neutrino. Second, neutrino oscillations solve another cosmic puzzle, the matter-antimatter asymmetry of the universe. The Big Bang should have created equal amounts of matter and antimatter, which would have subsequently annihilated each other, leaving behind a universe of pure energy. The fact that we exist in a universe made of matter means something must have tipped the scales. A process called leptogenesis, which relies on heavy, oscillating neutrinos in the early universe, is a leading candidate for how this might have happened, suggesting these tiny particles played an outsized role in making our material cosmos possible. Nowhere is the power of the neutrino more dramatically displayed than in a core collapse supernova. When a massive star runs out of fuel, its core collapses under its own immense gravity, crushing down into an ultra-dense neutron star or black hole in a matter of seconds. This collapse releases a titanic burst of energy, but that energy is trapped by the incredibly dense matter. It is the neutrinos, born in the unimaginable heat and pressure of the collapse, that become the star's salvation and its doom. Because they interact so weakly, they can escape the stellar core when even light cannot. In that final, explosive moment, the dying star releases more energy in neutrinos than the sun will emit in light over its entire 10 billion-year lifetime. For about 10 seconds, the neutrino flux from a single supernova in our galaxy would outshine the combined light of every star in the observable universe. It is this sudden loss of energy and pressure, carried away by the trillions upon trillions of fleeing neutrinos, that causes the outer layers of the star to rebound in the spectacular explosion we see from Earth. Furthermore, as these neutrinos oscillate on their way out of the collapsing star, they can drive exotic nuclear reactions, helping to forge many of the heavy elements that are essential for life, seeding the galaxy with the raw materials for future planets and ultimately living organisms. The neutrino, this nearly massless phantom particle, is not just a passive bystander but an active, essential sculptor of the cosmic landscape, its silent oscillations weaving the fabric of reality from the quantum world to the stellar scale. This concept of a seething, energetic vacuum, so crucial to the birth of the cosmos, isn't just a theoretical abstraction locked away in equations. We can actually reach out and touch its effects, measuring a tangible force that emerges directly from this restless quantum activity. This is the Casimir effect, a small but real pressure that appears when you bring two surfaces extraordinarily close together in a vacuum, providing one of the most compelling and direct pieces of evidence that so-called empty space is anything but. The effect is named after the Dutch physicist Hendrik Casimir, who, along with Dirk Polder, first predicted it in 1948. Casimir was working on problems related to colloidal chemistry, but his insight opened a window into a fundamental property of the universe. He realized that the quantum fluctuations we've been discussing are not all created equal. They can have different wavelengths, much like the different notes on a piano. In the open vacuum, every possible wavelength or note can exist, creating a rich symphony of virtual particle pairs appearing and vanishing. However, when you introduce two perfectly smooth, uncharged metal plates and place them just a few millionths of a meter apart, something fascinating happens to this symphony. The plates act like physical boundaries for the fluctuating electromagnetic fields. Think of them like the two fixed ends of a guitar string. The string can only vibrate in certain allowed modes, producing specific notes. Similarly, the space between the plates can only support quantum fluctuations whose wavelengths fit perfectly between the plates. Long wavelengths, those that are larger than the gap between the plates, simply cannot exist in that confined space. They are excluded. Outside the plates, however, the full spectrum of wavelengths continues to flourish unabated. This creates an imbalance in the radiation pressure of the vacuum. There are now more virtual particles pushing on the outside surfaces of the plates than there are pushing on the inside surfaces. The net result is an inward pressure, an attractive force that pushes the two plates together. It's not a force mediated by any of the four fundamental forces like gravity or electromagnetism in the traditional sense. It is a force born purely from the geometry of space itself and the reconfiguration of the quantum vacuum. For decades, the Casimir effect remained a theoretical curiosity, as measuring such a minuscule force between objects placed so close together without them touching was a formidable experimental challenge. The force is incredibly weak. For two plates 1 micrometer apart, the pressure is roughly equivalent to the weight of a single droplet of water spread over an area the size of a football field. But in 1997, physicist Steve Lamoureux at the University of Washington achieved a landmark measurement. His setup used a modern torsion pendulum, where one plate was fixed and the other was mounted on a sensitive arm that could rotate. As he moved the plates to within a micron of each other, he was able to directly measure the subtle twist caused by the Casimir force, confirming Casimir's 50-year-old prediction with remarkable precision. Since then, numerous other experiments have not only confirmed the effect but also explored its intricacies, such as how the force changes with different plate materials, shapes, and even when fluids are placed between them. This isn't a fringe observation, it's a reproducible phenomenon that confirms the physical reality of quantum zero-point energy. The implications of this reach far beyond a simple laboratory demonstration. As we push further into the realm of nanotechnology, building machines and circuits on the scale of individual molecules, the Casimir force moves from a quantum novelty to a critical engineering consideration. In the microscopic world, this vacuum pressure can be surprisingly strong, causing the tiny moving parts of a micro-electromechanical system, or MEMS, to unexpectedly stick together, a phenomenon known as stiction that can jam these delicate devices. Understanding and calculating the Casimir force is therefore essential for designing reliable nanoscale gears, actuators, and sensors. But the truly revolutionary potential lies in learning to manipulate it. Researchers are exploring ways to create quantum levitation by using materials with specific optical properties. If you could engineer a situation where the force between a plate and a different shaped object, like a sphere, becomes repulsive rather than attractive, you could, in theory, float nanoscale components on nothing but the pressure of the quantum vacuum itself, creating virtually frictionless bearings for the machines of the future. On a much grander, more speculative scale, the Casimir effect offers a tantalizing, though highly debated, clue to one of cosmology's biggest mysteries, the nature of dark energy. You'll recall that the cosmological constant, representing the energy density of the vacuum, is the leading explanation for the accelerating expansion of the universe. When theorists try to calculate the value of this vacuum energy by summing up all the possible quantum fluctuations, they run into a colossal problem. Their calculations produce a number that is 120 orders of magnitude. That's a 1 with 120 zeros after it, larger than the value observed through astronomy. It is arguably the worst theoretical prediction in the entire history of science. The Casimir effect shows us that we can indeed measure and manipulate the energy of the vacuum in a lab, and its measured value aligns perfectly with quantum electrodynamics. This tells us our understanding of the quantum vacuum is correct on small scales. The monumental discrepancy with the cosmological constant suggests there is something profound we are missing about how this vacuum energy behaves on the scale of the entire universe, or perhaps that dark energy is something else entirely. The humble Casimir force, measurable between two tiny plates, thus becomes a crucial bridge, connecting the confirmed, quirky physics of the very small to the deepest, unresolved mysteries of the very large, proving that the whispers of the quantum vacuum have something profound to say about the destiny of the cosmos. While we have been exploring forces tied to gravity and quantum fields, there is another invisible power threading its way through the cosmos, a force so familiar here on Earth yet wildly influential across the vastness of space: magnetism. We often think of magnets as things stuck to our refrigerators, but on a cosmic scale, magnetic fields are a fundamental architectural element, a pervasive energy that weaves through the vacuum, shaping the birth of stars, guiding the flow of galactic gas, and accelerating particles to nearly the speed of light. Unlike gravity, which always pulls, magnetic fields can push, twist, and channel, creating structure and complexity in the interstellar medium. They are the cosmic sculptors of ionized gas, the invisible architects of some of the most beautiful and violent processes in the universe. This grand magnetic influence begins in the turbulent nurseries where stars are born. A massive cloud of gas and dust collapses under its own gravity to form a new star, but it rarely does so in a simple, straightforward collapse. These clouds are magnetized, and as they contract, the magnetic field lines are dragged inward and wound up like an invisible spiderweb being pulled tight. This creates a powerful magnetic pressure that fights back against gravity, effectively putting the brakes on the collapse. It's a cosmic tug of war that determines the final mass of a star and whether it will be born alone or with a family of planets. In some cases, the field channels material into powerful jets that shoot out from the newborn star's poles, piercing through the surrounding cloud for light years. These spectacular outflows, visible as Herbig-Haro objects, act as a release valve, carrying away excess rotational energy and allowing the star to continue growing. Without this magnetic regulation, star formation would be a far more chaotic and inefficient process, potentially resulting in fewer, more massive stars and altering the entire life cycle of galaxies. Beyond stellar nurseries, the influence of magnetism expands to an even grander stage: the structure of entire galaxies. Our own Milky Way, like all spiral galaxies, is permeated by a large-scale magnetic field. This field isn't uniform, it's a complex web that follows the spiral arms, creating a cosmic guidance system for the interstellar medium. Charged particles like electrons and ions become trapped by these field lines, spiraling along them like beads on a wire. This has a profound effect on the dynamics of galactic gas. The magnetic fields provide a form of pressure that helps support giant molecular clouds against their own gravity, and they can also channel the flow of hot, ionized gas, helping to shape the majestic spiral arms we see. Perhaps most strikingly, these fields align the tiny, oblong dust grains that float in space, causing them to spin in a preferred direction. As these grains spin, they emit a faint radio wave that is polarized, allowing radio telescopes to map the galaxy's magnetic field lines directly. The resulting images reveal a stunning filamentary tapestry, a hidden skeleton of magnetic force woven through the entire galactic disk. One of the most dramatic demonstrations of cosmic magnetism is its role in accelerating particles to incredible energies, creating what we call cosmic rays. These are not rays of light, but rather atomic nuclei, mostly protons, that streak across the galaxy at nearly the speed of light. For a century, the origin of these ultra-high-energy particles has been a major puzzle. The leading explanation involves magnetic fields acting as nature's own particle accelerators, far more powerful than anything we can build on Earth. The process is thought to work through something called diffusive shock acceleration. Imagine a supernova remnant, the expanding shell of debris from a colossal stellar explosion, plowing through the magnetized interstellar gas at supersonic speeds. This creates a massive shock wave, a cosmic sonic boom. A charged particle, like a proton, can become trapped between the magnetic fields on either side of this shock front. Each time it crosses the shock, it gains a little more energy, bouncing back and forth like a rubber ball in a rapidly closing hallway. Over time, the magnetic fields within the shock front can whip these particles up to energies millions of times greater than those produced in the Large Hadron Collider, eventually flinging them out into the galaxy to travel for millions of years. These cosmic rays, once accelerated, are then guided across the galaxy by the Milky Way's vast magnetic web. Their paths twisted and turned until they lose all memory of their origin, creating a continuous, invisible rain of high-energy particles that constantly bathes our planet. The evidence for these immense magnetic structures is not just theoretical. We can see their effects in stunning astronomical visuals. When we observe distant galaxies or nebulae with radio telescopes, we can detect the signature of synchrotron radiation. This is the light emitted when high-energy electrons, often accelerated by the processes just described, spiral at relativistic speeds around magnetic field lines. The result is a beautiful, ethereal glow that often reveals intricate filaments and loops, tracing out the invisible magnetic architecture of the object. In the depths of intergalactic space, we even find evidence of magnetic fields in the vast voids between galaxy clusters. How such fields were generated and amplified to fill such enormous volumes of space is an active area of research, with theories pointing to their origins in the early universe, perhaps seeded by quantum fluctuations and then stretched and wound up by the motions of plasma over billions of years. From guiding the gentle collapse of a stellar nursery to orchestrating the most powerful particle accelerators in the galaxy, magnetic fields are a silent, pervasive, and dynamic force, proving that the universe is not only governed by gravity and quantum chance, but also by the long-range order and structure imposed by this fundamental, invisible influence. But our journey through the unseen now takes us into truly speculative territory, to a concept that seems to defy the cosmic speed limit set by Einstein himself. Welcome to the strange and controversial world of tachyonic fields. The name comes from the Greek word tachys, meaning swift, and it refers to a hypothetical class of particles that, if they exist, would always and forever travel faster than light. This idea immediately strikes a nerve with anyone familiar with physics, as Einstein's special relativity states that nothing with mass can ever reach or exceed the speed of light. As an object approaches light speed, its mass becomes infinite, and the energy required to push it further becomes infinite as well. Tachyons turn this idea on its head. They are conceived as particles that are born faster than light and can never slow down to subluminal speeds. For a tachyon, the speed of light is not a barrier to break through, but a minimum velocity from below which they are forbidden. The theoretical framework for such bizarre entities arises from a quirky reinterpretation of Einstein's famous equation. The energy of a normal particle is defined by its mass and momentum. For a particle with real, positive mass, this equation works perfectly. But if you were to mathematically plug in an imaginary number for the mass, a concept that seems nonsensical in the physical world, the equations suggest a particle could exist that gains energy as it slows down and loses energy as it speeds up. Its rest mass would be an imaginary number, but its energy and momentum could still be real and measurable as long as it forever travels faster than light. This isn't just science fiction, it's a self-consistent, if highly speculative, solution within the mathematics of quantum field theory. In this framework, a tachyonic field would represent an instability, a state of affairs that is fundamentally unsettled and eager to decay into a more stable configuration. Much like a pencil balanced perfectly on its tip is unstable and will inevitably fall over. This idea of instability leads to one of the most compelling potential roles for tachyonic fields in the story of the cosmos: their possible involvement in the process of cosmic inflation or spontaneous symmetry breaking in the early universe. Imagine the state of the universe in its first fleeting moments. It may have existed in a precarious, high-energy state, a kind of false vacuum. The presence of a tachyonic field could have triggered its rapid descent into a more stable, lower-energy state, the true vacuum we inhabit today. In this scenario, the tachyon isn't a particle zipping around in space, but rather a condition of the entire universe. The moment this tachyonic instability kicked in, it could have initiated the period of hyper-fast expansion we call inflation, or it could have been the mechanism that bestowed mass upon particles through the Higgs mechanism, a process where the Higgs field itself is thought to have undergone a tachyonic transition. In this view, the tachyon is not a thing, but an event, a sudden, universal shift that carved the fundamental forces and properties of matter out of a formless, symmetric beginning. However, the tachyon concept is shrouded in deep controversy and significant theoretical problems. The most glaring issue is causality, the principle that cause must always precede effect. If something can travel faster than light, then from certain perspectives, it could arrive at a destination before it even left its source. This opens the door to the possibility of time travel and paradoxes, like the famous grandfather paradox, where you could go back in time and prevent your own grandfather from meeting your grandmother, thereby preventing your own birth. Most physicists view such paradoxes as a clear sign that the theory is flawed or that our understanding is incomplete. Furthermore, no tachyon has ever been detected despite numerous searches for them. If they did exist and interact with ordinary matter even weakly, they would produce a unique and detectable form of radiation known as Cherenkov radiation in a vacuum, a kind of sonic boom of light. The fact that we see no evidence of this is a strong, though not definitive, argument against their existence as conventional particles. So, do tachyonic fields belong in the realm of legitimate physics, or should they be relegated to the pages of speculative fiction? The answer is nuanced. While the idea of faster-than-light particles as tangible entities we might one day detect is largely dismissed by the mainstream, the mathematical concept of tachyonic instabilities remains a valuable and active tool in theoretical physics. It provides a powerful language for describing phase transitions, not just in the early universe, but in condensed matter systems as well. The phenomenon is a powerful reminder that our exploration of the cosmos must sometimes venture into the mathematically possible, even if it seems physically improbable. These concepts push the boundaries of our understanding, forcing us to re-examine our most cherished principles and ask if the laws we hold as universal truths are indeed the final word, or merely a compelling chapter in a much longer, stranger story. Now, let's turn our attention to a concept that seems to pull a profound something from the absolute nothingness of space: vacuum energy. You might think of a perfect vacuum as a state of complete emptiness, a void totally devoid of energy or activity. But quantum physics paints a radically different picture. According to quantum field theory, every point in space, even in its lowest possible energy state, is still a hive of frantic, restless activity. This baseline energy, known as zero-point energy, is the absolute minimum, the ground state of a quantum field. It's the energy that remains when you remove every particle, every photon, and every measurable source of energy. Think of it as the constant, humming background noise of the universe, a fundamental jitter that can never be switched off, ensuring that true, absolute stillness is impossible. This isn't just a mathematical abstraction, it has real, observable consequences. The Casimir effect we discussed earlier is a direct manifestation of this zero-point energy. Those virtual particles popping in and out of existence are a direct result of the fields having this irreducible minimum energy. The energy involved is minuscule on human scales, but it's everywhere, permeating every cubic centimeter of the cosmos. When theoretical physicists attempt to calculate the total vacuum energy density by summing up the contributions from all the quantum fields, they run headlong into the most staggering discrepancy in all of science. The calculation, based on our well-tested understanding of quantum mechanics, suggests a vacuum energy density so colossal that it should have caused the universe to expand apart at such a ferocious rate that not even atoms could have formed. The number they get is a 1 followed by 120 zeros times larger than the value we actually observe for dark energy. This isn't a small error. It's a catastrophic failure of our theories to align with reality, a problem so severe it's known as the cosmological constant problem. This problem represents a fundamental chasm between our two most successful pillars of modern physics, quantum field theory and general relativity. Quantum field theory, which describes the very small, predicts a vacuum energy of immense magnitude. General relativity, which describes gravity and the cosmos on large scales, treats this vacuum energy as the cosmological constant, the simplest explanation for dark energy. The observed value of the cosmological constant, however, is incredibly tiny, almost but not quite zero. Reconciling the quantum prediction with the cosmological observation is arguably the single greatest challenge in theoretical physics today. It suggests one of two startling possibilities. Either our understanding of the quantum vacuum is profoundly incomplete, or there is a mysterious yet unknown cancellation mechanism that almost but not perfectly zeroes out the vacuum energy, leaving behind the faint residue we measure as dark energy. Some physicists propose a solution through the concept of the multiverse. In this controversial but compelling idea, our universe is just one of a vast, perhaps infinite, number of universes, each with different physical constants and laws. In most of these universes, the vacuum energy is indeed enormous, and those universes either collapse instantly or expand too rapidly for life to ever arise. We, of course, find ourselves in one of the rare, finely tuned universes where the cosmological constant is small enough to allow for the formation of galaxies, stars, planets, and ultimately, observers. This anthropic explanation is deeply unsatisfying to many scientists, as it moves the question from "why is the vacuum energy so small?" to "why are we in a universe where it is small?" Others seek a more fundamental physical solution, perhaps from a theory of quantum gravity like string theory, which might naturally explain the near cancellation. For now, vacuum energy remains a profound puzzle, a whisper from the quantum world that echoes through the vast expanse of the cosmos, reminding us that the nature of nothing itself is one of the most complex and mysterious frontiers in our quest to understand reality. After exploring the elusive nature of quantum fields and faster-than-light possibilities, we encounter a concept that bends the very geometry of the cosmos in a new way. Picture the universe in its first moments, a seething, ultra-hot soup of energy undergoing a series of rapid phase transitions, much like water freezing into ice. As the cosmos expanded and cooled, the fundamental forces we know today began to separate out from a unified state. In any such transition, imperfections can be frozen into the new, more stable state. In ice, you might get cracks or fissures. In the fabric of spacetime itself, one of the most dramatic possible imperfections is a cosmic string. Imagine a crack in reality, not as a void, but as an incredibly thin, unimaginably dense filament of pure energy, a one-dimensional flaw stretched across the universe. These hypothetical structures are termed topological defects, meaning their existence is tied to the overall shape or topology of the fields that pervaded the early cosmos. They are not made of matter as we know it. They are kinks in spacetime itself, relics of a more symmetric epoch, potentially as thin as a proton, but with the mass of a mountain range packed into every inch of their length. The formation of a cosmic string would be an event of profound violence, locked in during the universe's first fractions of a second. As the cosmos cooled, the Higgs-like fields responsible for fundamental forces settled into their lowest energy states. Think of this process like laying a carpet over a massive, uneven floor. For the most part, the carpet lies flat, but if the floor has a post sticking out of it, the carpet has to have a wrinkle or a tear emanating from that point. In the cosmic analogy, the post is a region where the field couldn't smoothly align with its surroundings. This misalignment gets stretched across the expanding universe, resulting in a cosmic string, a linear defect of concentrated energy that could be as long as the observable universe itself. Unlike a black hole, which is a point-like singularity, a cosmic string is a linear singularity. If one were to pass through this room, you wouldn't see it, but its incredible density would warp space around it in a unique and detectable way. The gravitational pull of a straight cosmic string is so peculiar that it wouldn't attract objects in the usual sense. Instead, it would create a conical distortion in space-time, like poking a hole in a piece of paper and bringing the edges together. This bizarre geometry leads to one of the most promising methods for detecting these space-time scars: gravitational lensing. We're familiar with the lensing effect of massive objects like galaxies, which bend light into arcs and rings. A cosmic string would produce a far more distinct signature. Because the space around a string is conical rather than curved, it wouldn't magnify background objects. Instead, it would create a perfect, unblurred double image of anything directly behind it. If a cosmic string drifted between us and a distant galaxy, we wouldn't see a smeared arc. We would see two identical, sharp copies of that galaxy, separated by a tiny, precise gap. Astronomers have meticulously scanned the skies for such telltale double visions, but so far, no confirmed case has been found. This lack of evidence has allowed scientists to place stringent limits on how many such strings could be crisscrossing the cosmos, suggesting that if they exist, they are either exceedingly rare or located far beyond our current observational reach. Beyond distorting the light from individual galaxies, a moving cosmic string would also leave an imprint on the oldest light in the universe, the cosmic microwave background. A string's immense mass density creates a gravitational potential well, but due to its unique geometry, this well has a very sharp edge. As the CMB radiation passes by a string moving at a significant fraction of light speed, photons skimming one side of the string would experience a slight blue shift, while those on the other side would be slightly redshifted. This would create a very specific, thin line of discontinuity in the CMB temperature map, a sudden, step-like change in temperature between two adjacent regions of the sky. This is often called the Kaiser-Stebbins effect. Searching for these faint, linear cracks in the afterglow of the Big Bang is another active area of research, with cosmologists using sophisticated statistical algorithms to comb through the exquisite data from satellites like Planck, looking for any anomalous straight-line features that can't be explained by standard cosmic structures. The potential influence of cosmic strings doesn't end with their subtle gravitational effects. In some theoretical models, these cosmic defects could have served as the primordial seeds for all the structure we see today. Before the widespread acceptance of cosmic inflation, cosmic strings were a leading candidate to explain how galaxies formed. The idea was that their immense gravity would act as condensation nuclei, pulling in the surrounding dark matter and normal matter to jump-start the collapse of the first protogalactic clouds. While inflation has since become the dominant paradigm for structure formation, it's not entirely mutually exclusive with cosmic strings. Some models of inflation and other early universe theories still predict their formation, albeit at a much lower density. Furthermore, if they exist, oscillating loops of cosmic strings would be powerful sources of gravitational waves, ripples in spacetime that could be detected by future observatories. The specific frequency and intensity of these waves would provide a direct probe into the physics of the universe's first moments, offering a glimpse into energy scales far beyond the reach of any particle collider. While still hypothetical, the search for cosmic strings continues to drive observational techniques to new heights, representing a thrilling intersection of cosmology's grandest theories with the painstaking hunt for the most subtle of cosmic clues. Moving from the grand, spacetime sculpting potential of cosmic strings, we dive into the realm of the incredibly small, to a hypothetical particle that might be so numerous and so stealthy that it could form the very dark matter halos holding galaxies together. This is the action, a light and ghostly particle born not from a desire to explain dark matter, but from a deep puzzle in the physics of the atomic nucleus. The problem is known as the strong CP problem, and it strikes at the heart of our understanding of the force that binds quarks together to form protons and neutrons. The strong nuclear force, described by a theory called quantum chromodynamics, appears to be surprisingly symmetrical. The C stands for charge conjugation, which means swapping particles for their antiparticles, and P stands for parity, which is like looking at the universe in a mirror. While other fundamental forces, like the weak nuclear force, clearly violate this CP symmetry, the strong force shows no sign of it whatsoever. This is deeply perplexing because, according to the mathematics, there is no fundamental reason why it shouldn't. This symmetry should be broken, leading to predictions of a neutron having a much larger electric dipole moment, a slight separation of positive and negative charge within it than we have ever observed. The measurements show the neutron is incredibly symmetrical, meaning this CP violation is either absent or tuned to zero with an accuracy of 1 part in a billion. This level of fine-tuning seems unnatural, as if the universe has chosen a very special, precise value for a fundamental parameter for no apparent reason. The action was proposed as an elegant solution to this conundrum. The theoretical mechanism, proposed by Roberto Pexi and Helen Quinn, and later developed by Frank Wilczek and Steven Weinberg, introduces a new field throughout the universe. The presence of this field dynamically cancels out the troublesome CP violating term, forcing the strong force to behave in the symmetrical way we observe. Just as the Higgs field gives particles their mass, this new field would have its own associated particle, the action. This particle would be exceptionally light, potentially billions of times lighter than an electron, and interact only very weakly with normal matter. In fact, actions could pass through entire planets as if they weren't even there. This very elusiveness, which makes them so difficult to detect, is also what makes them a perfect candidate for the mysterious dark matter that permeates the cosmos. If they exist, they would have been produced in colossal numbers in the hot, dense conditions of the early universe, forming a pervasive, cold cloud that could perfectly explain the gravitational effects we attribute to dark matter without the need for more massive, hypothetical particles. The search for these phantom particles is a feat of extreme experimental ingenuity. Unlike other dark matter candidates that might be detected through rare nuclear recoils, actions reveal themselves through a unique predicted phenomenon: their conversion into photons in the presence of a strong magnetic field. This process is the target of experiments like the Action Dark Matter E-experiment, or ADMX. Housed at the University of Washington, ADMX is essentially a super-sensitive radio receiver tuned to listen for the faintest whisper in the cosmos. At its heart is a powerful magnet that creates a strong magnetic field. Inside this field is a resonant cavity, a metal chamber that can be tuned to specific frequencies. The theory goes that if actions are indeed the dark matter, they are streaming through this cavity right now. In the presence of the magnet's field, a tiny fraction of these actions should convert into microwave photons. The frequency of these photons depends directly on the action's mass, which we don't know. So, the ADMX team slowly tunes the cavity, scanning through millions of possible frequencies, listening patiently for a faint, mono-energetic signal that would stand out against the background noise. It's like tuning a radio dial across the entire static field band, searching for one perfectly clear, quiet station that has never been heard before. The sensitivity required is almost beyond belief. The experiment must be cooled to near absolute zero to eliminate thermal noise, and its amplifiers are among the most quiet ever built, pushing the very boundaries of quantum measurement. While ADMX is a flagship effort, the hunt for actions is a global pursuit with a diverse array of strategies. Some experiments, like the International Action Observatory, use powerful magnets pointed at the sun, searching for actions that might be produced in the solar core. Others look for indirect astronomical signatures. For instance, actions streaming through the intense magnetic fields surrounding neutron stars could convert into observable radio waves. and astronomers are searching for unexplained excess emission from these dense stellar corpses. There is even the fascinating possibility that actions could be detected by their effect on light from distant quasars. If actions exist, they could couple to photons and cause a slight rotation in the plane of polarization of this light as it travels across billions of light years through intergalactic magnetic fields. Each of these methods probes a different possible property of the action, creating a multi-pronged effort to trap this most elusive of cosmic phantoms. The discovery of an action would be a monumental event in physics, simultaneously solving a deep theoretical puzzle in the Standard Model and identifying the major component of the dark matter that has shaped the cosmos. It would reveal a universe teeming with invisible particles that are fundamental to the structure of both the infinitesimally small quantum world and the astronomically large galactic landscape. This fine-tuning of the cosmos leads us to a profound and often debated question. Why is the universe structured in such a way that it allows for our existence? This line of inquiry brings us to the anthropic principle, a concept in cosmology that attempts to grapple with the astonishingly precise values of the fundamental constants of nature. Consider the force of gravity, the strength of the nuclear forces, or the mass of an electron. If any of these values were altered by even a tiny fraction, the universe as we know it would be impossible. If the strong nuclear force were just a few % stronger, hydrogen would be unstable and stars could not burn. If it were slightly weaker, complex elements necessary for planets and life would never form. The expansion rate of the universe is equally delicate. Had it been a minuscule bit faster, matter would have flown apart too rapidly for galaxies to coalesce, and had it been a tiny bit slower, the universe would have collapsed back on itself long before life could emerge. This remarkable balance is what we call the fine-tuning problem, and the anthropic principle is a framework for thinking about why we find ourselves in a universe that seems so perfectly tailored for our presence. The principle itself comes in two primary forms, starting with the weak anthropic principle. This is a relatively straightforward, almost logical statement. The conditions in the universe must be compatible with the existence of observers because we are here to observe them. It's a selection effect. Imagine a puddle of water waking up one morning and thinking, "This hole I'm in fits me perfectly. It must have been designed precisely for my shape." The puddle doesn't realize that it's the one that has conformed to the shape of the hole, not the other way around. Similarly, the weak anthropic principle suggests that we should not be surprised to find the constants of nature set to life-permitting values, because in a universe where they weren't, we would not exist to be surprised about anything. We are, in a sense, cosmic lottery winners, living in one of the rare regions of space and time where the conditions just happen to line up for life to evolve. This version of the principle is widely accepted as a useful, almost tautological tool that reminds scientists to account for observational biases in their cosmological theories. Then there is the strong anthropic principle, which takes a much more radical and controversial stance. It proposes that the universe must have properties that allow life to develop within it at some stage in its history. The word "must" is key here, implying a form of necessity or design. This version often ventures into philosophical and even theological territory, suggesting that the existence of observers is a fundamental constraint on the nature of the cosmos. Proponents might argue that this points toward a universe with a purpose, or that consciousness is not just a happy accident but an integral part of its functioning. Critics, however, argue that the strong anthropic principle is not a scientific statement at all, as it is untestable and unfalsifiable. It doesn't provide a physical mechanism for why the universe must be life-friendly. It simply asserts it as a given which can halt further scientific inquiry. For many physicists, this makes the strong version an unsatisfying explanation, a conversation stopper rather than a path to deeper understanding. A powerful alternative that brings the anthropic principle back into the realm of testable science is the concept of the multiverse. If our universe is just one of a vast, perhaps infinite, ensemble of universes, each with its own unique set of physical laws and constants, then the fine-tuning mystery begins to dissolve. In this sprawling cosmic landscape, the vast majority of universes would be stillborn or sterile, with constants set to values that prevent the formation of atoms, stars, or planets. But in a tiny, statistically inevitable fraction of these universes, the numbers would, by pure chance, fall into the narrow window that permits complexity and life. We, of course, find ourselves in one of those exceptionally rare, life-friendly universes simply because we couldn't exist anywhere else. The multiverse idea transforms the question from why is our universe so special to we necessarily observe a universe that seems special to us. This framework is compelling to many because it replaces the need for a single, finely tuned universe with a vast, random population where our existence becomes a statistical certainty rather than a miracle. Yet, the debate over the anthropic principle's scientific validity remains intense and unresolved. On one hand, it has proven useful in addressing specific cosmological puzzles. For instance, before the discovery of dark energy's small but non-zero value, some physicists used anthropic reasoning within a multiverse model to predict that the cosmological constant should be just large enough to allow galaxies to form but not so large that it rips the universe apart before life can arise, a prediction that aligns surprisingly well with our subsequent measurements. On the other hand, many scientists remain deeply uncomfortable with anthropic reasoning, fearing it can be used to explain away any problem without offering a concrete, predictive mechanism. They argue that the goal of physics should be to find a single, elegant theory that uniquely predicts the constants we see, not to invoke an unobservable infinity of other worlds. The principle sits at a fascinating crossroads between physics, philosophy, and epistemology, forcing us to confront the limits of scientific explanation and the profound role of the observer in shaping our understanding of a reality that, against staggering odds, allowed us to be here to see it. But if the forces we've explored so far operate across vast distances or permeate all of space, our next phenomenon presents a connection so intimate and instantaneous that it seems to defy the very concept of distance itself. This is quantum entanglement, a concept so bizarre that even Einstein famously derided it as spooky action at a distance. At its heart, entanglement is a profound link that can form between two or more particles, a bond so deep that their fates become permanently intertwined regardless of the space that separates them. Imagine creating a pair of electrons in such a way that their properties are linked. For instance, a fundamental property of a particle is its spin, which you can picture very loosely as a tiny arrow that can point either up or down. In the entangled pair, the total spin must always be zero, meaning if one particle has spin up, the other must have spin down. This in itself isn't so strange. The true magic, the genuine spookiness, reveals itself when you separate the two particles. Let's say you take one of these entangled electrons with you on a journey to a distant star, thousands of light years away, while your partner keeps the other here on Earth. The moment you arrive, you decide to measure the spin of your electron. The instant you do, you force it to choose a definite state. Let's say you find it is spin up. At that exact same moment, you know with absolute certainty that the electron back on Earth has just snapped into the opposite state, spin down. This knowledge isn't communicated. It's an instantaneous correlation that happens faster than light could possibly travel between you. It's as if the two particles are not two separate entities, but a single, unified system that exists as one, even when its parts are scattered across the galaxy. This phenomenon has been confirmed through countless meticulous experiments, often using pairs of entangled photons. Researchers have separated these photons and measured their properties like polarization at detectors placed many kilometers apart. The results are unequivocal. The measurement of one photon instantly determines the state of its partner, with a correlation that simply cannot be explained by any hidden, pre-existing information. The universe, at its most fundamental level, appears to be non-local, with connections that transcend our everyday understanding of space and separation. This bewildering behavior forced a major schism in the early days of quantum theory. Einstein, Podolsky, and Rosen, in their famous EPR paper, argued that this spooky action was evidence that quantum mechanics was an incomplete theory. They believed there must be some hidden variables, unseen factors that predetermine the particle's states all along, thus preserving a local, classical reality where no influence could travel faster than light. For decades, this was a philosophical debate. Then, in the 1960s, physicist John Bell devised a brilliant mathematical theorem that could, in principle, test whether these hidden variables could exist. Bell's inequality established a clear threshold. If the correlations between entangled particles exceeded this threshold, it would rule out any local hidden variable theory, confirming that the spooky action was real. When experiments were finally performed with the necessary precision, most famously by Alain Aspect and his team in the 1980s, the results were clear and decisive. The quantum correlations violated Bell's inequality. The universe had chosen the spooky path. There are no hidden local variables. The particles are genuinely connected in a way that defies our classical intuition, and measurement itself seems to play an active role in defining reality. While the philosophical implications are staggering, the practical applications of this quantum weirdness are now beginning to reshape technology. The most prominent of these is quantum computing. A classical computer bit is like a simple light switch. It can only be either a 0 or a 1. A quantum bit or qubit exploits the principles of superposition and entanglement. Because of superposition, a qubit can be both 0 and 1 simultaneously, like a switch that is both on and off at the same time. Now, when you entangle multiple qubits, their states become interdependent. This creates an exponential explosion in computational power. 2 entangled qubits can represent 4 states at once, 3 qubits can represent 8 states, and 300 qubits could represent more states than there are atoms in the known universe. This parallelism allows a quantum computer to explore a vast number of possibilities simultaneously, solving certain problems that would take today's most powerful supercomputers billions of years to crack. They could revolutionize fields like drug discovery by simulating complex molecular interactions, break current forms of encryption, and optimize logistical systems for global supply chains. Entanglement also forms the backbone of the emerging field of quantum cryptography, specifically through a protocol called quantum key distribution. Imagine 2 people, traditionally called Alice and Bob, who want to share a secret message. They can generate a stream of entangled photon pairs, with Alice keeping one from each pair and Bob taking the other. They then measure the polarization of their respective photons, and because of entanglement, their measurement results will be perfectly correlated. This correlation becomes their unbreakable secret key. The true beauty of this system is its inherent security. If an eavesdropper, Eve, tries to intercept the photons to learn the key, she is forced to measure them. But in the quantum world, measurement disturbs the system. Eve's interference will inevitably introduce errors and anomalies in the correlation between Alice and Bob's results, alerting them immediately to the presence of a spy. This isn't just a mathematical security, it's a security guaranteed by the fundamental laws of physics, creating a truly secure communication channel. Yet, for all its utility, the deepest mystery of entanglement remains unanswered. How does this instantaneous connection actually work? It's crucial to understand that this is not a signal. You cannot use entanglement to send a faster-than-light message. While the correlation is instantaneous, the outcome of any single measurement is completely random. The person on Earth measuring their electron sees a random result, up or down, with no way of knowing if their partner across the galaxy has just made a measurement or not. The spookiness is only apparent when the two observers later come together and compare their notes, finding that their random results are perfectly correlated in a way that defies classical explanation. The prevailing interpretation is not that information is traveling, but that the entangled particles do not possess definite properties until they are measured. They exist in a shared, fuzzy reality, and the act of measurement solidifies that reality for both of them at once, no matter the distance. This suggests a profound holism to the universe, where what we perceive as separate objects are, at a quantum level, deeply and inseparably linked parts of a single entangled whole. It forces us to reconsider the very nature of reality, hinting that the fabric of the cosmos may be woven from threads of connection that operate on a level far deeper and more mysterious than the space-time continuum we call home. Yet, if the bizarre connections of quantum entanglement challenge our understanding of a single reality, the next concept shatters the idea entirely, proposing that our entire cosmos is just one bubble in an infinite, frothing ocean of universes. This is the multiverse, a staggering proposition that what we call the universe, everything we can possibly observe, is merely a tiny region within a much vaster and more diverse meta-reality. This isn't a single, unified theory, but rather a collection of ideas emerging from the frontiers of cosmology and quantum physics, each pointing toward the existence of other realms, potentially with entirely different laws of physics. The motivation for such a radical idea often stems from the same fine-tuning puzzles we encountered with the anthropic principle. The fundamental constants of nature appear so exquisitely balanced for life that it seems like a cosmic miracle, but the multiverse offers a natural, if mind-bending, explanation. If every possible value for these constants occurs in some universe, then it's no wonder we find ourselves in one where the numbers are just right for us. One of the most compelling pathways to the multiverse comes from the theory of cosmic inflation. You'll recall that our universe is thought to have undergone a period of exponential expansion in its first moments. The leading models suggest that this inflationary process may not have been a one-time event that started and stopped everywhere at once. Instead, it might be eternal. Picture the fabric of spacetime as an endlessly rising loaf of raisin bread, where each raisin is a region like our own universe. In most of this loaf, the inflationary energy field continues to drive rapid expansion, stretching spacetime at an incredible rate. However, in random spots, this field decays, converting its immense energy into a hot soup of particles and radiation. Each of these decayed regions becomes a pocket universe, a bubble like our own, disconnected from all the others due to the hyper-fast expansion of the inflating space between them. In this eternal inflation scenario, the overall meta-universe is constantly giving birth to new bubble universes, an unending process creating an infinite multiverse where our entire cosmic history is just a single episode in a never-ending story. While eternal inflation paints a picture of countless cosmic bubbles, a completely different path to the multiverse emerges from the strange world of quantum mechanics. This is the many worlds interpretation proposed by Hugh Everett in the 1950s. It tackles the central mystery of quantum physics. Why do we only ever see a single, definite outcome when the mathematics describes a particle existing in multiple simultaneous states, a superposition? The standard Copenhagen interpretation says that this superposition collapses into one reality when we observe it. Everett's radical alternative suggests that no collapse ever occurs. Instead, every time a quantum event has multiple possible outcomes, the entire universe splits or branches into multiple copies, with each possible outcome realized in a new parallel world. In one world, the electron you measured has spin up. In the newly branched world, an identical version of you measures it as spin down. This isn't a physical splitting in space, but a continual branching of the entire quantum state of reality. Every choice, every random quantum event, from the decay of an atom to the firing of a neuron in your brain, would generate new, equally real timelines, creating a mind-numbingly vast tree of parallel histories. The philosophical implications of these ideas are as profound as they are unsettling. If the multiverse is real, it redefines our place in the cosmos, transforming us from the intended products of a single, finely tuned universe into inevitable inhabitants of one lucky branch in an infinite ensemble. The concept of probability itself begins to warp. In the many worlds view, every outcome with a non-zero probability happens in some branch. The version of you reading this script might have driven a different car to work today, or perhaps a version exists where you never were born at all. This can lead to a sense of existential vertigo, seemingly diminishing the significance of our choices if every alternative is played out somewhere else. Yet, it also offers a powerful, non-supernatural answer to the fine-tuning problem. We don't need to ask why our universe's constants are so perfect for life. In an infinite multiverse, every possible combination of laws exists somewhere. We simply must find ourselves in one of the rare habitable pockets because we couldn't exist in the overwhelming majority that are sterile or stillborn. However, the multiverse concept is not without its fierce critics and formidable challenges. The most significant is the issue of falsifiability. If these other universes are permanently disconnected from our own by vast stretches of inflating space or by existing in separate quantum branches, can we ever gather empirical evidence for them? Many scientists argue that a theory that cannot be tested, even in principle, lies outside the realm of science. Proponents counter that the multiverse is not a theory in itself, but a prediction of other, well-developed theories like inflation and quantum mechanics. They search for indirect, subtle clues within our own universe. For instance, if our cosmos collided with another bubble universe in the distant past, it might have left a unique, circular imprint on the cosmic microwave background, a kind of cosmic bruise. While tantalizing hints have been reported, no such definitive evidence has been confirmed. Other physicists worry about the theory of anything problem. If the multiverse allows for every conceivable set of physical laws, then it risks predicting everything and therefore explaining nothing, making it impossible to derive specific, testable predictions about our own world. The debate over the multiverse strikes at the very heart of what we mean by a scientific explanation. Is it enough for a theory to be mathematically elegant and to provide a natural, compelling framework for puzzling observations, even if direct observation is impossible? Or must a scientific idea be subject to experimental verification to be considered valid? This tension ensures the multiverse remains one of the most controversial and thrilling frontiers in modern cosmology. It pushes our imagination to its absolute limit, forcing us to contemplate a reality of literally cosmic proportions, where the entirety of our existence, with all its beauty, complexity, and history, might be just one single thread in an infinite and breathtaking tapestry of all possible realities. When we consider the origin of the most enigmatic objects in the cosmos, our minds might turn to the dramatic deaths of massive stars, collapsing in supernova explosions to leave behind stellar mass black holes. But there exists a far more ancient and elusive possibility, a class of black holes that could have been forged not from dying stars, but from the raw, seething energy of the universe's very first moments. These are primordial black holes, hypothetical remnants from the dawn of time that could silently make up the dark matter that binds galaxies together, or they could be mere cosmic phantoms, a fascinating idea without physical form. Their formation story is completely different from their stellar cousins. While a stellar black hole requires a star many times more massive than our Sun to exhaust its fuel and collapse, a primordial black hole could have been born from the intense density fluctuations present in the primordial fireball. In the incredibly dense and hot conditions just after the Big Bang, random overdensities lumps of energy and matter could have become so compressed that their own gravity caused them to directly collapse, bypassing the entire stellar life cycle entirely. It's a concept that suggests the universe might have been seeding its darkness from the very beginning. The potential mass range for these ancient objects is one of their most intriguing features. They are not constrained by the mass limits of stellar collapse. A primordial black hole could be almost unbelievably small, with a mass equivalent to a modest asteroid yet compressed into a region smaller than a single proton. Conversely, they could be as massive as thousands of suns or even larger. This flexibility makes them compelling candidates for the universe's missing mass. For decades, the leading hypothesis for dark matter has been some kind of exotic, undiscovered particle, like the WIMP or the action. But despite decades of searching, no such particle has been conclusively detected. This persistent lack of evidence has led some scientists to re-examine the possibility that at least a portion of dark matter could be made of these primordial black holes. They would be the ultimate dark matter candidate, massive, purely gravitational, and nearly impossible to see directly, perfectly explaining the gravitational pull we observe without emitting or interacting with light. So, how could we possibly hope to find something that is, by its very nature, invisible? Astronomers have devised several clever methods to catch these phantoms in the act. One of the most powerful techniques is gravitational microlensing. This relies on Einstein's theory of general relativity, which tells us that a massive object will warp the spacetime around it, bending any light that passes nearby. If a primordial black hole were to drift through space and pass almost directly in front of a distant background star from our viewpoint here on Earth, its gravity would act as a tiny lens. For a brief period, it would focus and amplify the star's light, causing it to temporarily brighten in a very specific and recognizable way. The duration of this brightening event is a clue to the mass of the lensing object. A black hole with the mass of a planet might cause a brightening that lasts for a few hours, while one with the mass of a star could brighten the background star for several weeks. Projects like the optical gravitational lensing experiment have monitored hundreds of millions of stars for years, searching for these telltale flashes. They have found numerous microlensing events, but the great challenge is proving that the lens was a black hole and not a faint, dim star or a free-floating planet. The data so far has largely ruled out the possibility that primordial black holes of around a stellar mass make up all of the dark matter, but the door remains open for them to constitute a significant fraction, especially at higher or lower mass ranges. Beyond their potential role as dark matter, these ancient objects could also be the source of the gravitational wave signals we are now routinely detecting. When LIGO and Virgo first heard the chirp of two black holes merging, one of the immediate questions was about their origin. The masses of some of these merging black holes were surprisingly large, sitting in a range that is somewhat difficult to explain through standard stellar evolution. Could some of these be primordial black holes dating back to the universe's infancy? If so, their merger history would be different from stellar black holes. They wouldn't need to be born in binary star systems. They could have been formed in close proximity in the dense early universe or been captured into orbits around each other much later in cosmic history. The specific distribution of their masses, spins, and merger rates, as we gather more and more data from gravitational wave observatories, could eventually provide a statistical fingerprint that distinguishes primordial black holes from stellar remnants. Every new cosmic collision we detect adds another data point, helping us to piece together the true ancestry of the dark population of black holes that seem to populate the cosmos. The search for these relics is not confined to distant stars or the ripples in spacetime. Some scientists have proposed that a very small primordial black hole, one with a mass similar to a large mountain, could potentially pass through our solar system. Its gravitational tug would subtly perturb the orbits of the planets, and while no such definitive anomaly has been found, it remains a tantalizing possibility. Other theories suggest that if a low-mass primordial black hole were to collide with a body like a neutron star, it would be absorbed and would rapidly consume the star from the inside out, releasing a distinctive burst of radiation. The continued non-detection through these various channels is in itself a valuable scientific result, allowing researchers to gradually narrow down the possible mass windows where primordial black holes could still be hiding. Whether they are proven to be real or are eventually ruled out, the investigation into primordial black holes forces us to confront the wild and unpredictable conditions of the universe's birth, a time when the fabric of reality itself may have knotted into tiny points of infinite density, seeding the cosmos with a hidden darkness that has endured for billions of years. As we chart the course of our own Milky Way and its neighbors through the cosmos, astronomers have uncovered a puzzling and relentless drift, a mysterious tug that seems to be pulling our entire galactic neighborhood toward a specific point in the void. This is the enigma of the Great Attractor, a colossal gravitational anomaly located in the direction of the Centaurus and Norma constellations, roughly 150 million light-years away. For decades, its true nature remained shrouded behind a veil of our own galaxy, lying directly in what astronomers call the zone of avoidance. This region of the sky is obscured by the dense gas, dust, and brilliant stars of the Milky Way's galactic plane, making observations of the universe beyond incredibly difficult. It's like trying to see a distant mountain range through a thick, perpetual fog. Yet, despite this cosmic blindness, we knew something massive was there because of its unmistakable gravitational pull on the motion of hundreds of thousands of galaxies, including our own. The initial evidence for this mysterious pull came from meticulous studies of galaxy motions. When scientists mapped the velocities of galaxies relative to the overall expansion of the universe, they expected to see a relatively uniform flow. Instead, they found a startling deviation. Our local group of galaxies, along with a vast swath of space millions of light-years across, is being drawn inward at a staggering velocity of several hundred kilometers per second toward this unseen focal point. This collective motion is known as bulk flow, and the scale of it pointed toward a concentration of mass so immense that it defied easy explanation. At first, some speculated it could be a previously unknown supercluster or an enormous agglomeration of dark matter. However, the estimated mass required to produce such a powerful tug was far greater than any known structure in that part of the universe. The Great Attractor wasn't just a large cluster of galaxies. It appeared to be a gravitational focal point of almost mythical proportions, a cosmic whirlpool pulling in everything around it. A crucial breakthrough in understanding this phenomenon came with the discovery of an even larger and more massive structure hidden behind the Great Attractor itself, the Laniakea supercluster. Using sophisticated techniques to map the velocities of thousands of galaxies, researchers were able to trace the gravitational watershed of our cosmic neighborhood. They defined a supercluster not just as a group of galaxies that are close together, but as all the galaxies flowing together along lines of gravitational force toward a common center. This new map revealed that our Milky Way is but a tiny suburb on the outer fringe of an immense cosmic metropolis now named Laniakea, a Hawaiian word meaning immense heaven. This structure spans an incredible 500 million light-years and contains the mass of 100,000 Milky Way galaxies. The Great Attractor is not the final destination, but rather a dense gravitational anchor point within Laniakea, a major hub in the vast superhighway of galactic motion. It is the central gravitational valley into which the entire supercluster is slowly draining, but the story of cosmic flows doesn't end with Laniakea. Observations of galaxy clusters at even greater distances have revealed hints of something more extensive and puzzling, a phenomenon known as dark flow. This is the suggestion that entire clusters of galaxies, scattered across billions of light years, are moving in a coherent, uniform direction that cannot be explained by the gravitational influence of any known matter in the observable universe. It's as if there is a vast, unseen structure outside our observable horizon, exerting a gravitational pull on everything inside it. While the evidence for dark flow remains controversial and is hotly debated within cosmology, its potential existence would force a radical rethinking of our standard model. It could imply that the inflationary period that birthed our universe left behind an irregularity on a scale far larger than we can see, or that our universe is but one bubble in a multiverse, and we are feeling the gravitational tug of a neighboring cosmic bubble. The Great Attractor, then, might be just the local manifestation of a much grander and perhaps fundamentally unknowable architectural feature of reality. For a long time, the core of the Great Attractor remained a mystery, hidden behind the zone of avoidance. However, modern technology has begun to pierce through this galactic fog. While optical telescopes struggle to see through the dust and stars of the Milky Way's disk, other forms of light can penetrate it. Infrared observatories like NAS, a wide-field infrared survey explorer, can peer through the obscuring dust to reveal galaxies lurking behind it. Even more powerful are radio telescopes, which use long-wavelength radiation that is largely unaffected by interstellar dust. Surveys using radio telescopes have painstakingly mapped the hidden universe behind the zone of avoidance, and what they found was not one single monstrous object, but an even more complex and dense confluence of mass. The core of the Great Attractor is now known to be the Norma Cluster, an incredibly dense knot of galaxies, and the surrounding region is one of the most massive concentrations of matter in our entire cosmic vicinity. This reveals that the Great Attractor is not a singular, inexplicable entity, but a predictable, though exceptionally massive, node in the cosmic web, the point where several vast filaments of dark matter and galaxies intersect, creating a deep gravitational well that dictates the motion of everything in our local supercluster. This grand perspective fundamentally changes how we see our own place in the cosmos. We are not drifting aimlessly. Our galaxy, along with its neighbors, is on a long, slow cosmic migration, following the invisible contour lines of gravity shaped primarily by dark matter. This journey is measured in billions of years. The Great Attractor is not pulling us in to consume us. It is simply the heart of our gravitational continent, the center of mass toward which we are inevitably, slowly falling. This realization connects the largest scales of the universe directly back to the fundamental force of gravity and the hidden architecture of dark matter. It shows us that the cosmos is not static, but a dynamic and flowing entity, with vast rivers of galaxies streaming along preordained paths, their motion dictated by the unseen cosmic forces that have been sculpting reality since the very beginning. While we have explored the immense gravitational pull of the Great Attractor, there is another, far more intimate cosmic force that constantly bombards our planet, a silent rain of atomic fragments traveling at nearly the speed of light. These are cosmic rays, and despite their name, they are not rays of light at all, but rather high-energy particles, mostly single protons and atomic nuclei streaking across the galaxy. Every second, thousands of these invisible projectiles pierce through your body, utterly harmless, yet they carry within them the stories of the most violent and energetic events in the universe. Their origins are a tale of cosmic power, tracing back to the shockwaves of exploding stars and the frenzied hearts of distant galaxies, and their journey ends by creating a beautiful, ethereal light show in our own upper atmosphere, while providing scientists with a unique probe into physics at its most extreme. The quest to understand where these particles get their incredible speed leads us directly to the remnants of supernova explosions. When a massive star ends its life in a cataclysm, it doesn't just vanish, it leaves behind an expanding shell of debris hurtling outward at supersonic speeds. This creates a colossal shock wave, a cosmic sonic boom that plows through the surrounding interstellar gas. This shock front is tangled with powerful magnetic fields, and it is here that nature operates its most powerful particle accelerator. The process, known as diffusive shock acceleration, works like a subatomic pinball machine. A charged particle, like a proton, can become trapped between the approaching shock front and the turbulent magnetic fields ahead of it. Each time the particle crosses the shock boundary, it gains a significant boost in energy. It gets bounced back and forth countless times, ricocheting off the magnetic irregularities, and with each pass it picks up more speed. Over years or centuries, this relentless process can whip a single proton up to energies millions of times greater than what we can achieve in the Large Hadron Collider, until finally, the magnetic fields can no longer contain it, and it gets flung out into the galaxy as a cosmic ray, destined to travel for millions of years. But supernova remnants are not the only cosmic engines capable of such feats. For the very highest energy cosmic rays, those with energies so vast they are nicknamed "Oh my God" particles, we must look to even more monstrous sources. The prime suspects are active galactic nuclei, the intensely bright cores of distant galaxies powered by supermassive black holes. As vast quantities of matter spiral into the black hole's accretion disk, it becomes superheated and generates powerful jets of plasma that shoot out from the galactic core at nearly the speed of light, stretching for thousands of light years. The turbulent magnetic fields within these relativistic jets are thought to be capable of accelerating particles to energies that dwarf even those from supernova. These ultra-high-energy cosmic rays are incredibly rare. Only a handful strike each square kilometer of Earth's atmosphere per century. Determining their exact origin is one of the great challenges in astrophysics, as their paths are bent and scrambled by the Milky Way's own magnetic fields during their long journey, erasing any clear pointer back to their source. When these galactic visitors finally reach Earth, they initiate a spectacular cascade of light and matter in our sky, a process that happens entirely unseen by our naked eyes. A single high-energy cosmic ray proton, moving at a breathtaking 99.99% of the speed of light, will slam into a molecule of nitrogen or oxygen at the top of our atmosphere. The collision is so violent that it shatters the nucleus of the air molecule and creates a shower of secondary particles, pions, muons, electrons, and positrons. These newly created particles, themselves traveling at relativistic speeds, then collide with other atmospheric nuclei, creating even more particles. The result is an expanding avalanche of billions of secondary particles, all descending toward the ground in a wide, pancake-like disk. This entire event is called an extensive air shower. As the charged particles in this shower, particularly the electrons and positrons, travel faster than the speed of light in air, they produce a faint, fleeting flash of bluish light known as Cherenkov radiation. This is the same phenomenon that causes nuclear reactors to glow with an eerie blue light in water. Giant, specialized telescopes with incredibly sensitive cameras, like those at the Pierre Auger Observatory in Argentina, are designed to detect this faint, ultraviolet Cherenkov glow, allowing us to indirectly see the cosmic ray and measure its original energy and direction. Beyond their role as natural particle accelerators, cosmic rays serve as an invaluable tool for physicists, allowing them to probe fundamental laws under conditions impossible to recreate in a lab. When these high-energy particles collide with atmospheric nuclei, they create a miniature fireball that replicates for a fleeting instant the conditions of the universe just moments after the Big Bang. From this energy, new and exotic particles can bloom into existence. In fact, the first antimatter particle ever discovered, the positron, was found in cosmic ray air showers back in 1932. Modern particle physics was born in these atmospheric interactions, and even today, studying the products of these high-energy collisions helps us test the limits of the standard model and search for hints of new physics. Furthermore, because cosmic rays are charged, their paths are twisted and bent by the interstellar and intergalactic magnetic fields they traverse. By studying the arrival directions and energies of millions of cosmic rays, scientists can attempt to map the invisible magnetic architecture of our galaxy, using these particles as probes to trace out the lines of force in the cosmic web. They are messengers that have traveled across the galaxy, and encoded in their energy and type is a map of the magnetic storms and violent events that have shaped their epic journey, offering us a unique way to perceive the invisible forces that structure the cosmos. But what if our universe's dramatic birth in a single Big Bang was not the beginning of everything, but merely one chapter in an endless cosmic cycle? This is the provocative heart of the ekpyrotic universe model, a theory that dares to reimagine the origin of our cosmos not as a singular, explosive event, but as the result of a colossal, yet silent, collision between realms of reality existing in a higher dimensional space. The name ekpyrotic comes from the ancient Greek word for conflagration, or out of fire, yet this model describes a far more structured and less violent beginning than the primordial fireball of the traditional Big Bang. It emerged from the framework of string theory, which suggests that the fundamental constituents of reality are not point-like particles but tiny, vibrating strings, and that our universe may be a three-dimensional brane, short for membrane, existing within a higher dimensional bulk. In this view, our entire cosmos is like a single, vast sheet of paper floating in a grand, multidimensional library. The cyclical nature of the ekpyrotic model offers a stunning alternative to the standard narrative. Instead of a universe exploding from an infinitely dense singularity and expanding forever into cold darkness, this theory proposes an endless sequence of cosmic epochs. The cycle begins with two parallel, mostly empty branes. Think of them as the walls of a higher dimensional chamber, slowly drifting toward each other across the bulk. They are cold, quiet, and stretched thin. There is no singularity, no point of infinite density. When these two branes finally collide, the impact does not create a fireball in the traditional sense. Instead, the immense kinetic energy of the collision is converted directly into the hot, dense soup of particles and radiation that we identify as the hot Big Bang. The universe as we know it is born from the shock of this contact, not from a singular point, but across a vast, uniform surface. This initial condition naturally explains the horizon problem that inflation was designed to solve, because the colliding branes were in a state of thermal equilibrium before they ever touched. The resulting universe begins with the same temperature everywhere. After the collision, the branes bounce apart, and our universe expands and evolves much as in the standard model, forming galaxies and stars until dark energy takes over and drives a long period of accelerated expansion. But the story doesn't end there. Eventually, the branes are drawn back together by a mysterious force, perhaps a spring-like tension in the bulk, setting the stage for the next collision and the next cosmic rebirth in an infinite, repeating loop. This vision stands in stark contrast to the traditional inflationary Big Bang picture. While inflation posits a brief, ultra-rapid expansion that smooths and flattens the universe from a tiny, chaotic speck, the ekpyrotic scenario suggests that the smoothness and flatness were inherent properties of the pre-collision brane. The universe didn't need a period of hyper-fast stretching to become uniform. It was born that way from the orderly, large-scale collision of two flat, parallel surfaces. This difference has profound implications for one of cosmology's most sought-after signatures, primordial gravitational waves. Inflation, occurring at incredibly high energies, is predicted to generate a strong background of these space-time ripples, which would leave a distinct curl-like pattern known as B-mode polarization in the cosmic microwave background. The ekpyrotic model, however, is a much gentler process. The collision and the ensuing expansion are not violent enough to produce a significant background of these primordial waves. The ongoing, meticulous search for this specific signal in the CMB is therefore a crucial test. If such waves are definitively found, it would be a major victory for inflation. If, however, they continue to elude detection, the ekpyrotic model and other alternatives gain significant credibility. One of the most compelling aspects of the ekpyrotic universe is its elegant handling of the cosmic singularity, the point of infinite density and temperature that marks the beginning of time in the standard Big Bang model. For physicists, a singularity is a sign that a theory has broken down, that our understanding of gravity, as described by general relativity, is incomplete. The ekpyrotic model offers a potential escape from this conundrum, because the universe is born from a collision of two brains that were already large and cold. There is no moment of infinite density. The Big Bang is not the absolute beginning, but a transition, a bridge from a previous cosmic phase. This provides a tantalizing potential pathway to unite the physics of the very large with the physics of the very small, as the behavior of the brains and the bulk could be described by a fundamental theory of quantum gravity, like string theory, avoiding the mathematical infinities that plague the standard cosmological model. It transforms the Big Bang from a wall at the beginning of time into a doorway to a deeper, cyclical reality. Naturally, such a radical proposal comes with its own set of challenges and open questions. Critics point out that the model relies on several speculative elements from string theory, which itself remains unverified. The nature of the bulk dimension, the forces that draw the brains together and pull them apart, and the precise mechanism of energy transfer during the collision are all areas of active research and debate. Furthermore, while the model elegantly explains the universe's uniformity, it must also account for the tiny imperfections that seeded galaxy formation. In the ekpyrotic scenario, these primordial density fluctuations are thought to be generated by quantum fluctuations in the field that governs the distance between the two brains as they approach each other. The resulting pattern of fluctuations is slightly different from that predicted by inflation, offering another potential observational test as our maps of the cosmic microwave background become ever more precise. The ekpyrotic universe model ultimately forces us to expand our conception of reality, suggesting that our entire cosmic history is but one episode in an endless, timeless cycle of creation, destruction, and rebirth, where the end of one universe is merely the quiet prelude to the beginning of the next. And now we arrive at the greatest unsolved problem in all of theoretical physics, a fundamental schism at the very heart of our understanding of reality. For over a century, we have been living with two extraordinarily successful but utterly incompatible descriptions of the cosmos. On one hand, we have Einstein's general relativity, a majestic theory that describes the force of gravity as the elegant curvature of spacetime itself. It perfectly predicts the orbit of Mercury, the bending of starlight, and the existence of black holes. It is the theory of the very large, of planets, stars, and galaxies. On the other hand, we have quantum mechanics, the bizarre and wildly accurate framework that governs the world of the atom. It describes a probabilistic, fuzzy reality where particles can be in two places at once and are connected by spooky entanglement. It is the theory of the very small. The problem is, these two titans of physics cannot coexist peacefully. In the most extreme environments in the universe, like the central singularity of a black hole or the very first moment of the Big Bang where immense gravity meets subatomic scales, the equations of general relativity break down completely, producing nonsensical infinities. Resolving this conflict is the holy grail of modern physics, and the quest to do so is the search for a theory of quantum gravity, a single, unified framework that can describe all of nature's forces under one roof. One of the most prominent and elaborate attempts to solve this puzzle is string theory. This approach makes a radical departure from the traditional view of the universe's most basic building blocks. For centuries, we have imagined particles as tiny, dimensionless points, String theory proposes that at the heart of every electron and every quark is not a point, but an unimaginably small, vibrating loop or filament of energy, a string. These strings are so minute that if an atom were the size of our solar system, a string would be the size of a single tree on Earth. The theory's beautiful core idea is that the different vibrational patterns of these strings are what give rise to the different particles we observe. Think of a guitar string. Pluck it one way and you get one note, pluck it another and you get a different note. In precisely the same way, one vibrational mode of a fundamental string might correspond to an electron, while another, higher energy mode might manifest as a photon, the particle of light. In this elegant picture, gravity emerges naturally from the theory in the form of a specific vibration called the graviton, a hypothetical particle that would mediate the gravitational force, just as the photon mediates the electromagnetic force. However, this elegant concept comes with some profound and mind-bending implications. For the mathematics of string theory to be consistent and free of those dreaded infinities, it requires something our everyday experience rebels against: extra dimensions of space. We are familiar with the 3 dimensions of space: length, width, and height, and 1 dimension of time. String theory, in its various forms, demands a universe with 10 or even 26 dimensions. So where are these extra dimensions? The leading idea is that they are compactified or curled up into a space so incredibly tiny, on the scale of the strings themselves, that they are completely hidden from our perception. A simple analogy is a garden hose. From a distance, it looks like a one-dimensional line, but if you were an ant crawling on its surface, you would discover a second dimension curled around the hose's circumference. In string theory, the 6 or 7 extra dimensions are thought to be curled up into an intricate, complex geometric shape known as a Calabi-Yau manifold. The specific shape of this hidden geometry would determine the properties of the particles and forces we observe in our 4-dimensional world, meaning the entire structure of our reality could be a consequence of the geometry of unseen dimensions. A very different and equally fascinating approach to the quantum gravity problem is loop quantum gravity. If string theory attempts to unite all forces by reimagining what matter is, loop quantum gravity takes a more direct path by focusing exclusively on quantizing space and time themselves. The central idea here is that space is not a smooth, continuous backdrop, as envisioned by Newton and Einstein, but is instead composed of tiny, discrete, indivisible packets or atoms of space. Picture the fabric of reality not as a seamless sheet of silk, but as a weave of 1 trillion tiny, interconnected loops. These loops form a network of relationships, a spinning, dynamic web often called a spin network. At the smallest possible scale, the Planck length, which is 1/trillionth of the size of an atomic nucleus, space is not smooth but granular, a foamy, buzzing structure. Time, in this view, may also be quantized, meaning that the universe evolves in the tiniest, discrete ticks of a fundamental clock, not as a continuous flow. This has a stunning consequence for the Big Bang. In loop quantum gravity, the universe could not have been crushed into an infinitely dense point. Instead, the theory suggests a big bounce, where a previous contracting universe reached a maximum density and then rebounded into the expanding universe we inhabit today, completely avoiding the mathematical nightmare of a singularity. Comparing these two giants reveals a fascinating philosophical split in how science confronts the unknown. String theory is a top-down approach. It starts with a grand, unifying principle that everything is made of vibrating strings and aims to derive all of particle physics and gravity from that single beautiful idea. Its strength is its ambition to be a theory of everything. Its major challenge, beyond the lack of any direct experimental evidence so far, is the existence of a vast landscape of possible solutions. The different ways to compactify the extra dimensions may lead to 10 to the 500 different possible universes, each with their own physical laws, making it difficult to explain why our particular universe has the properties it does. Loop quantum gravity, by contrast, is a bottom-up approach. It doesn't try to unify all forces at once. It focuses squarely on quantizing gravity and the geometry of space, using the well-established principles of quantum mechanics. Its strength is its mathematical rigor and its direct confrontation with the nature of space-time. Its challenge is that it has so far had more difficulty incorporating the other fundamental forces and the particles of the standard model with the same natural elegance as string theory. The ultimate test for any theory of quantum gravity will be an experimental one. Can they make predictions that we can actually observe? For string theory, one hope lies in the high-energy collisions of particle accelerators like the Large Hadron Collider. While we are far from the energies needed to see strings directly, some models predict we might detect evidence of extra dimensions through the creation of microscopic black holes or certain missing energy signatures. For loop quantum gravity, a key prediction involves the cosmic microwave background. The theory suggests that the primordial light from the Big Bang might bear subtle imprints of the granular, quantum nature of spacetime from the universe's first moments. Furthermore, both theories have profound things to say about black holes. They both predict that the entropy of a black hole, a measure of its information content, is related to the surface area of its event horizon, a result first discovered by Jacob Bekenstein and Stephen Hawking. Understanding the quantum microstates that give rise to this entropy is a major focus of research, as it touches on the deepest paradoxes of information and reality. While a definitive experiment remains on the horizon, the very pursuit of quantum gravity is already reshaping our conception of reality, suggesting that space and time themselves may be emergent properties, born from a deeper, more fundamental layer of existence that we are only just beginning to fathom. This idea leads us to one of the most profound and mind-bending concepts in all of theoretical physics, the holographic principle. It proposes a radical reimagining of reality, suggesting that our universe, with its rich, three-dimensional tapestry of galaxies, stars, and planets, might actually be a projection, a kind of cosmic hologram encoded on a distant, two-dimensional surface. The information required to describe everything we see and experience, from the flight of a bird to the spin of a galaxy, could be entirely contained on this lower dimensional boundary, much like a three-dimensional hologram is encoded on a flat, two-dimensional piece of film. This isn't just a philosophical musing, it's a serious hypothesis that emerges directly from the fiery crossroads of gravity, quantum mechanics, and the thermodynamics of black holes. The story of the holographic principle begins not with holograms, but with the most enigmatic objects in the cosmos, black holes. In the 1970s, a young physicist named Jacob Bekenstein made a startling proposal that challenged the established view of these dark giants. He argued that black holes must have entropy. Entropy is a measure of disorder or randomness, and in thermodynamics, it is also a measure of the information content within a system. The more disordered something is, the more information is needed to describe its microscopic state. Bekenstein realized that when matter carrying entropy falls into a black hole, it vanishes from our observable universe. To preserve the second law of thermodynamics, which states that the total entropy of the universe never decreases, the black hole itself must gain an equivalent amount of entropy. He calculated that this entropy was not proportional to the black hole's volume, as one might expect for a three-dimensional object, but to the surface area of its event horizon, the spherical point of no return. This was a bizarre and revolutionary insight. It suggested that the maximum amount of information a region of space can contain is not related to how much volume it has, but to the area of its boundary. Stephen Hawking initially disliked this idea, but his own subsequent work on quantum fields in curved spacetime ended up confirming and refining it. Hawking discovered that black holes are not completely black. Due to quantum effects near the event horizon, they emit a faint glow of radiation and slowly evaporate over astronomical timescales. This Hawking radiation posed a deep puzzle. What happens to all the information that fell into the black hole? If the black hole evaporates completely, does that information vanish forever, violating a fundamental tenet of quantum mechanics that information must be preserved? This became the infamous black hole information paradox. The holographic principle emerged as a potential solution. If the information about everything that has ever fallen into a black hole is not stored in its hidden interior, but is instead encoded on the surface of its event horizon, then when the black hole evaporates via Hawking radiation, that information could, in principle, be radiated back out, scrambled but not destroyed. The event horizon acts like a vast cosmic hard drive, storing the data of its contents in tiny, Planck-sized pixels on its two-dimensional surface. This profound connection between black hole physics and information theory was formalized by physicist Gerard T. Hooft and later developed by Leonard Susskind into the full-blown holographic principle. They extended Bekenstein's area law idea from black holes to the entire universe. The principle states that a description of all the physics within a volume of space can be perfectly encoded on a lower dimensional boundary surrounding that volume. For our universe, this would mean that the three spatial dimensions we experience plus time could be a projection from a vast two-dimensional surface at the cosmic horizon. We are, in essence, living inside a hologram. The world we perceive as solid and three-dimensional would be akin to the three-dimensional image that shimmers above a credit card security strip. The true, fundamental reality is the two-dimensional code on the strip itself. In this view, space-time and gravity are not fundamental but emergent phenomena, arising from complex quantum interactions happening on this distant boundary. The most concrete realization of this principle is the anti-de Sitter/conformal field theory correspondence, often abbreviated as ADS/CFT, proposed by physicist Juan Maldacena in 1997. This is a precise mathematical duality. It states that a theory of gravity in a hypothetical five-dimensional universe known as anti-de Sitter space is completely equivalent to a conformal field theory, a particular type of quantum field theory without gravity, living on its four-dimensional boundary. This is a full, exact equivalence, a dictionary that translates problems in one world into problems in the other. A difficult calculation involving the formation of a black hole in the five-dimensional gravitational world might translate into a much more manageable calculation involving the thermal properties of a hot plasma in the four-dimensional quantum world. ADS/CFT provides a firm mathematical foundation for the holographic principle, demonstrating that at least in certain theoretical universes, holography is not just a metaphor but a rigorous, calculable reality. What would this mean for our understanding of the cosmos? The implications are staggering and challenge our most basic instincts about reality. If the holographic principle is correct, then the apparent continuity of space and the smooth flow of time are illusions. The universe would have a finite information content with a fundamental resolution limit, much like a digital image has a finite number of pixels. This could provide a natural way to resolve the infinities that plague the quest for a theory of quantum gravity, as space-time itself would be pixelated at the tiniest possible scale. Furthermore, it suggests a deep and unexpected unity in the laws of physics. The long-sought quantum theory of gravity may not be a theory of gravity and spacetime at all, but rather a theory without gravity or spacetime that lives on a lower dimensional boundary from which our familiar four-dimensional universe, complete with Einstein's general relativity, miraculously emerges. We are left with a cosmos that is both profoundly strange and elegantly simple, where the dizzying complexity of our three-dimensional world is nothing more than a shadow cast by a deeper, simpler reality written on the fabric of the cosmic horizon. This staggering mismatch, known as the cosmological constant problem, stands as arguably the most severe and embarrassing failure of theoretical physics to align with observed reality. To truly grasp the depth of this problem, let's put these numbers into perspective. The vacuum energy density predicted by quantum field theory is a number so colossal it's almost impossible to visualize. It is 10 to the power of 120 times larger than the value we actually observe for dark energy. That's a 1 followed by 120 zeros. The observed vacuum energy driving the accelerated expansion of the universe is equivalent to just a few hydrogen atoms per cubic meter of space, a whisper-thin residue. The prediction, however, is a number of such immense magnitude that it should have caused the infant universe to expand with such ferocious violence that not even the simplest atoms could have ever coalesced. The fact that we exist in a stable, structured cosmos with galaxies and planets means something is profoundly wrong or profoundly misunderstood in our most fundamental theories. The heart of the crisis lies in the tragic incompatibility between our two most successful pillars of modern physics, quantum field theory and general relativity. Quantum field theory, which describes the behavior of particles and forces with breathtaking accuracy, tells us that the vacuum is a seething, energetic foam. When physicists perform the straightforward calculation to sum up the contributions from all the quantum fields, the zero-point energy of every possible vibration and fluctuation, they arrive at that impossibly huge number. This is not a flawed calculation. It's what the math of our best theories of the small-scale world directly implies. General relativity, Einstein's magnificent theory of gravity and the large-scale cosmos, then takes this vacuum energy and treats it as the cosmological constant. This constant represents a uniform energy density inherent to empty space itself, which generates a repulsive gravitational effect. The observed acceleration of the universe fits perfectly with a very small, positive cosmological constant. The catastrophe is that the number supplied by quantum physics is 120 orders of magnitude too large. It's as if you asked for a single grain of sand and were instead delivered a mountain larger than the entire observable universe. This is not a minor rounding error. It is a chasm of misunderstanding so vast it suggests we are missing something essential about the nature of reality. One proposed solution is that there exists a mysterious, perfect cancellation mechanism. Perhaps there is some undiscovered symmetry or principle in physics that causes the positive and negative contributions to the vacuum energy to almost exactly cancel each other out, leaving behind only a tiny, non-zero remainder that we see as dark energy. The problem with this idea is the word almost. Why would the cancellation be so exquisitely precise, leaving a leftover of just the right size to become dominant 14 billion years after the Big Bang, but not so perfect that it zeroes out completely? This requires another layer of fine-tuning that seems just as miraculous as the original problem. It's like two immense opposing forces, each with the power to destroy a continent, balancing on a knife's edge to produce a net force gentle enough to push a toy boat across a pond. This profound fine-tuning is what leads many physicists to consider the radical solution of the multiverse. In this controversial but compelling framework, our universe is just one of a vast, perhaps infinite, ensemble of universes, each with different physical constants and laws. In the overwhelming majority of these universes, the vacuum energy is indeed enormous, and those cosmos either collapse instantly into a big crunch or inflate apart so rapidly that no structure ever forms. We, of course, can only find ourselves in one of the incredibly rare universes where the cosmological constant is small enough to allow for the slow, patient growth of galaxies, stars, and planets, and ultimately, conscious life that can ponder its own existence. This anthropic explanation is deeply unsatisfying to many scientists because it doesn't provide a fundamental physical mechanism for why the constant is small. It simply states that we must observe a universe where it is small. It moves the question from the domain of physics to the domain of statistics and observational selection, which feels to some like giving up on a deeper explanation. Other researchers suggest the problem indicates that our very concept of gravity is flawed on cosmological scales. Perhaps Einstein's general relativity, while exquisitely accurate within our solar system, is not the final theory of gravity. It may be an approximation that breaks down when applied to the universe as a whole. Modifications to gravity, such as theories involving extra dimensions or new fields, attempt to explain the observed cosmic acceleration without invoking any vacuum energy at all, thereby sidestepping the problem entirely. These theories must carefully walk a tightrope, reproducing all the successful predictions of general relativity in local contexts, while altering its behavior on the largest scales to account for the acceleration we see. So far, no modified gravity theory has achieved widespread acceptance as a more compelling solution than the cosmological constant, but the search continues, driven by the sheer magnitude of the problem. The cosmological constant problem is more than just a puzzle. It is a glaring signpost pointing toward a deeper layer of reality, a fundamental truth about the union of the quantum and the cosmic that we have not yet uncovered, reminding us that for all our knowledge, the universe still holds its most profound secrets close. But just when we think we understand the grand, uniform structure of our universe, an anomaly emerges from the data, a ghost in the machine so perplexing that cosmologists gave it a name fit for a supervillain, the axis of evil. This is not a literal axis in space, but a bizarre and unexpected pattern found in the most pristine map of the infant universe, the cosmic microwave background radiation. According to our fundamental cosmological principle, the universe should be isotropic and homogeneous when viewed on a large enough scale. This means it should look the same in every direction, with no preferred center, no special axis, and no grand distinguishing features. The cosmic microwave background, the afterglow of the Big Bang, is our best evidence for this. It paints a picture of a remarkably smooth and uniform early cosmos, with only the tiny, random temperature fluctuations that seeded future galaxies. Yet when scientists probed deeper into this map, they found something that sent a shiver through the world of cosmology. The fluctuations weren't completely random. They seem to be subtly aligned along a particular preferred direction in space, a cosmic equator that should not exist. The discovery of this alignment came from meticulous analysis of the data collected by NAS, a Wilkinson Microwave Anisotropy Probe, or WMAP, and later confirmed with even greater precision by the European Space Agency's Planck satellite. Researchers were looking at the largest scales of the CMB map, the patterns that stretch across the entire sky. They were studying multipole moments, which are mathematical ways of describing the distribution of hot and cold spots. The quadrupole, which describes the most basic elliptical deviations from a perfect sphere, and the octupole, which describes more complex cloverleaf-like patterns, showed a startling correlation. Their warm and cold spots weren't oriented randomly. Their planes were aligned with each other. Even more strangely, this alignment also seemed to be related to the ecliptic plane of our own solar system and the direction of our solar system's motion through the cosmos. It was as if the universe's earliest imprints were somehow aware of our local celestial neighborhood, a connection that defies all conventional logic and makes absolutely no sense within the standard model. The immediate and most conservative explanation is, of course, that the axis of evil is a statistical fluke combined with an unaccounted-for systematic error. When you have a dataset as vast as the full sky CMB map, you are bound to find some strange-looking patterns purely by chance. It's the cosmic equivalent of seeing a face in the clouds. The human brain is wired to find patterns even where none truly exist. Furthermore, meticulously cleaning the raw data from foreground contamination is an immensely complex task. The glow from our own Milky Way galaxy, dust, and other local sources must be subtracted with incredible precision to reveal the pristine CMB signal underneath. Perhaps the argument goes our data cleaning methods are not perfect. There might be a subtle, residual foreground signal or an instrumental artifact that imprinted this peculiar alignment, making it look like a feature of the early universe when it is really just a smudge on our cosmic lens. Many cosmologists hold this view, believing that as our measurements become ever more refined, this strange axis will eventually fade into the background noise. Yet the anomaly has proven stubbornly persistent. The Planck satellite, with its superior sensitivity and resolution, confirmed the basic features of the alignment, even after extensive reanalysis and different approaches to foreground removal. This persistence has forced scientists to consider more exotic possibilities, ideas that venture beyond the standard cosmological model. One such proposal involves the pre-inflationary universe. Cosmic inflation is the theory that the universe underwent a period of hyper-fast expansion, which should have blown away any pre-existing structure, leaving the cosmos smooth, flat, and without a preferred direction. But what if inflation didn't start from a perfectly symmetrical state? What if the universe that gave birth to inflation had some primordial structure, a kind of crystalline geometry or a preferred direction woven into the fabric of space-time itself? In this scenario, the axis of evil could be a relic, a fossil from the epoch before inflation, a scar that was stretched to cosmic proportions but never completely erased. It would be a window into a realm and a time we thought were forever lost, a hint of the universe's true initial conditions. Another, even more mind-bending possibility involves the very large-scale structure of the cosmos and our place within it. The alignment of the CMB patterns with our solar system's motion is particularly difficult to explain. This motion creates a Doppler shift, making the CMB appear very slightly hotter in the direction we're moving and cooler in the opposite direction. This dipole is a well-understood local effect, but the axis of evil seems to have a connection to this dipole that goes beyond a simple coincidence. This has led some to speculate that the anomaly is not in the CMB itself, but in the space-time between us and the surface of last scattering. Perhaps the universe is not uniform on scales even larger than we can observe. Our observable universe might be part of a much larger, inhomogeneous structure, and we are experiencing a large-scale gravitational effect, like a vast tidal force from beyond the horizon, that is subtly distorting the CMB light on its 14 billion-year journey to us. This would mean the axis of evil is not a feature of the early universe, but a shadow cast by a colossal, unseen mass distribution in the cosmos, challenging the cosmological principle itself. The implications of the axis of evil being real are profound. It would mean our universe has a preferred direction, a fundamental asymmetry that would force a rewrite of our most basic cosmological textbooks. The standard model of cosmology, the lambda cold dark matter model, is built upon the foundation of isotropy. If that foundation has a crack, the entire elegant structure might need revision. It could point toward new physics, perhaps a modification to Einstein's gravity or a more complex model of inflation. For now, the axis of evil remains an unsolved mystery, a tantalizing and controversial clue etched into the oldest light we can see. It serves as a powerful reminder that our maps of the cosmos, for all their breathtaking detail, may still contain profound surprises, and that the universe continues to guard its deepest secrets with a mischievous and puzzling grin. While our galaxy may appear as a serene, spinning disk of stars when viewed from afar, it holds violent secrets in its core, and evidence of a past cataclysm was only recently discovered emanating from its very heart. Stretching an astonishing 25,000 light-years above and below the galactic plane, two colossal orbs of intense gamma-ray radiation stand as silent monuments to a forgotten eruption. These are the Fermi bubbles, first discovered in 2010 by scientists analyzing data from NASA's Fermi Gamma-Ray Space Telescope. Before this discovery, our view of the galaxy's central regions was cluttered with the glow of individual pulsars and supernova remnants. It took sophisticated analysis to subtract this foreground noise and reveal the faint but immense outline of these twin structures, each one holding the energy equivalent of 100,000 supernova explosions. They form a ghostly hourglass figure centered on the supermassive black hole known as Sagittarius, a star, a pair of cosmic lungs that seem to breathe out high-energy particles across a volume of space encompassing half the visible Milky Way. The leading hypothesis for the creation of these gigantic bubbles points directly to a period of intense activity from our galaxy's central supermassive black hole. While Sagittarius, a star, is relatively quiet today, it may have experienced a dramatic feeding frenzy in the past. The scenario is one of cosmic violence on an almost unimaginable scale. A vast cloud of gas, or perhaps a stray star, ventured too close to the black hole's event horizon and was torn apart by immense tidal forces. As this material spiraled into the accretion disk, it became superheated to millions of degrees, and a portion of it was funneled by intense magnetic fields into two powerful, opposing jets that shot out from the black hole's poles at nearly the speed of light. These jets punching through the galactic gas would have inflated the Fermi bubbles over a period of several million years, filling them with a soup of relativistic particles. The gamma rays we detect are the afterglow of this event, produced when these high-speed electrons interact with light and interstellar gas, a process known as inverse Compton scattering. However, a competing and equally compelling theory suggests the bubbles could be the cumulative remains of a different kind of starburst event. In this model, the galactic center experienced a period of frenzied star formation, leading to the birth and subsequent death of many massive stars in a relatively short cosmic time frame. These stars would have lived fast and died young, exploding as supernova in quick succession. The combined shock waves from hundreds or thousands of these simultaneous explosions could have created a superwind, a titanic outflow of energy that blew the interstellar material outward, carving the very cavities we now observe as the Fermi bubbles. This starburst hypothesis is supported by the presence of other structures near the galactic center, like the X-ray emitting chimneys and the microwave haze, which could all be part of the same complex, multi-phase outflow from a singular, energetic epoch in the Milky Way's history. Regardless of their precise origin, the Fermi bubbles act as a powerful and long-lasting record of our galaxy's dynamic past. They are a fossil imprint of a time when the Milky Way was a much more active and violent place. By studying their size, shape, and the spectrum of their emissions, astronomers can effectively perform galactic archaeology, piecing together the timeline of this ancient eruption. The sharp, well-defined edges of the bubbles suggest the outburst was relatively short and intense, a brief scream in the galaxy's multi-billion-year life, rather than a continuous, slow leak of energy. Their continued presence also reveals crucial information about the structure of the galaxy's magnetic field and the nature of the gaseous halo that surrounds the entire Milky Way, providing a unique laboratory to study how galaxies interact with their environment and expel material into intergalactic space. The discovery and ongoing investigation of the Fermi bubbles has fundamentally altered our understanding of galactic ecology. It demonstrates that even seemingly quiescent galaxies like our own are capable of immense, energetic outbursts that can reshape their structure on a grand scale. These events are crucial for regulating star formation, as the outflowing material can heat or blow away the cold gas required to form new stars, effectively placing a limit on a galaxy's growth. The bubbles are a stunning reminder that our cosmic home is not a static island universe, but a living, breathing, and occasionally volatile system, whose history is written not only in its stars, but in the vast, invisible structures that tower over its disk. They stand as a testament to the immense forces slumbering in the heart of every galaxy, forces that can, when awakened, leave scars across the cosmos that endure for millions of years. Yet while we look outward to the cosmic forces shaping galaxies and the universe, a more immediate and human-made danger is accumulating right here in the space around our own planet, a looming predicament known as the Kessler syndrome. Imagine a single collision between two pieces of space junk, perhaps a defunct satellite and a discarded rocket stage, smashing into each other at over 17,000 miles per hour. This impact doesn't just create two new pieces of debris, it creates hundreds, even thousands of shards, each one a high-velocity projectile. Now, each of those fragments has the potential to strike another object in orbit, generating even more debris in a catastrophic chain reaction. This is the essence of the Kessler syndrome, a theoretical cascade where the density of objects in low Earth orbit becomes so high that collisions become self-sustaining, creating an ever-growing cloud of shrapnel that could render entire orbital regions unusable for generations. It's a domino effect of destruction where one accidental impact could potentially slam the door on humanity's future in space. The sheer scale of our orbital clutter makes this scenario frighteningly plausible. Right now, space around Earth is far from empty. Tracked by global space surveillance networks, there are over 30,000 objects larger than a softball whizzing around our planet, and millions more smaller fragments that are too tiny to monitor effectively but still travel with the energy of a hand grenade. This includes everything from dead satellites and spent rocket bodies to flecks of paint, frozen coolant, and tools dropped by astronauts. All of it is trapped in a relentless cosmic ballet, with different objects occupying different orbital highways, from the busy low Earth orbit used by the International Space Station and many Earth observation satellites, to the higher geostationary orbit crucial for global communications and weather monitoring. The velocity involved is the real killer. Even a paint chip traveling at orbital speeds carries more kinetic energy than a high-powered rifle bullet, capable of puncturing spacecraft hulls, shattering solar panels, or disabling critical systems. The implications of a full-blown Kessler syndrome event would be nothing short of a global economic and technological crisis. Our modern way of life is deeply dependent on the infrastructure floating silently above us. A severe debris cascade in low Earth orbit could destroy countless satellites that provide us with GPS navigation, precise weather forecasting, global communications, and essential Earth monitoring for climate science and disaster response. The International Space Station and any future space stations would become vulnerable fortresses, their crews in constant peril from unseen projectiles, requiring frequent and hazardous maneuvers to avoid tracked debris. But perhaps the most profound consequence would be the effective quarantining of space itself. Launching new satellites or crewed missions would become an incredibly high-risk endeavor, like trying to sail a boat through a hurricane of shrapnel. A runaway cascade could create a lethal barrier, trapping humanity on Earth and halting our expansion into the solar system for centuries, until the slow drag of the upper atmosphere finally cleansed the orbit over many decades. Addressing this silent threat requires a multi-pronged approach, a global effort in cosmic housekeeping. The first and most critical step is mitigation, preventing new debris from being created in the first place. International guidelines now urge satellite operators to design their spacecraft with passivation systems that vent leftover fuel and discharge batteries at the end of their life, reducing the risk of explosion. There is also a growing push for post-mission disposal rules, which require satellites in low Earth orbit to be equipped with enough propellant to deorbit themselves, burning up in the atmosphere after 25 years or less, or to be moved up to a less congested graveyard orbit if they operate much higher. Yet guidelines are not laws and compliance is not universal. The real challenge lies in active debris removal, the technological equivalent of fishing for bullets in a storm. Concepts being studied include harpoons, nets, robotic arms, and even lasers to nudge debris toward the atmosphere. These missions are complex, expensive, and still in their infancy, but they represent our only hope for cleaning up the mess we have already made and preventing a runaway chain reaction that could forever change our relationship with the final frontier. But for all the grand cosmic forces we've explored, from dark energy to gravitational waves, perhaps none captures the human yearning for connection beyond our world more powerfully than a single, fleeting event that lasted just 72 seconds. It was a summer evening in 1977 at Ohio State University's Big Ear radio telescope, which was methodically scanning the sky as part of the long-running search for extraterrestrial intelligence, or SETI. The telescope's output was a string of alphanumeric characters printed on continuous fanfold paper, representing the signal strength across 50 channels. The next day, a volunteer named Jerry Amon was dutifully reviewing the previous night's data when his eye caught something that made him catch his breath. On the printout, next to a sequence of numbers indicating an incredibly intense narrowband radio burst, he circled the string 6EQUJ5 and wrote in the margin in red ink a single emphatic word: "Wow." This brief annotation gave the signal its immortal name, and it remains, over 4 decades later, the most compelling and enigmatic candidate for a potential alien transmission ever detected. What made the WOW signal so extraordinary were its specific, seemingly artificial characteristics. First, it was a narrowband signal, concentrated on a single frequency of 1420.406 MHz. This is significant because natural cosmic objects typically emit radio waves across a broad spectrum of frequencies, like the static hiss of a radio tuned between stations. A narrowband signal, in contrast, is the hallmark of an engineered transmitter designed to punch through the cosmic noise with maximum efficiency. Second, the signal was incredibly strong. The intensity reading peaked at a value of 30 sigma, meaning it was 30 times louder than the background noise surrounding it, an astonishingly powerful burst. Third, it exhibited the telltale signature of a celestial source. Because the Big Ear telescope used a fixed reflector with 2 feed horns, any signal from space would appear, grow stronger, and then fade as the Earth's rotation carried it first through one horn and then, a few minutes later, through the other. The WOW signal displayed this exact profile, appearing in one horn for 72 seconds and then, as expected, being absent from the second horn's data for a subsequent check before presumably reappearing. This confirmed it came from the sky, not from a passing airplane or a terrestrial source of interference. The immediate and obvious question was, and still is, what was it? The leading natural explanations have all faced significant challenges. Could it have been a signal reflected off a piece of human-made space debris? The frequency of 1420 MHz is a protected band, reserved exclusively for radio astronomy, meaning no earthly transmitters should have been actively using it. Furthermore, a reflection would not have exhibited the clean, celestial drift curve that the WOW signal possessed. Another possibility is that it was an emission from a cometary hydrogen cloud. Decades later, one researcher proposed that 2 comets, which happened to be in the same region of sky, could be the culprits. However, this theory was widely dismissed by astronomers who pointed out that comets are not known to emit strong, narrowband radio signals at that specific frequency. The signal's location in the constellation Sagittarius points toward the dense center of our own Milky Way galaxy, a region teeming with stars, but no known type of star or other astrophysical phenomenon has ever been observed to produce such a brief, powerful, and spectrally pure radio burst before or since. Its one-off nature is a huge part of the mystery, despite numerous and extensive follow-up observations by Amon and others. The signal never repeated. The enduring fascination with the WOW signal lies in this perfect storm of properties that align so well with what scientists predicted an intentional interstellar broadcast might look like. If an advanced civilization wanted to get the attention of a newly technological species like ourselves, sending a brief, powerful hello on a universally recognized frequency would be a logical approach. The chosen frequency, 1420 MHz, is particularly suggestive because it is one of the main emission lines of neutral hydrogen, the most common element in the universe. It's often called the water hole, a metaphorical watering place where galactic civilizations might naturally gather to communicate. The signal's temporary nature could be explained if it was a targeted beacon that swept past our solar system, only briefly illuminating us as it swung through its arc, much like a lighthouse beam briefly flashes on a ship at sea. The profound silence that followed could mean we simply missed our one brief window to listen, or that the transmitter was never aimed our way again. This single, unverified event has had an outsized impact on the scientific and cultural pursuit of answers to humanity's oldest question, are we alone? It provided a tangible, data-driven reason to take the search for extraterrestrial intelligence seriously, fueling the development of more sophisticated and sensitive radio telescope arrays for decades to come. Projects like the SETI Institute's Allen Telescope Array are in many ways spiritual successors to the Big Ear, designed to monitor millions of channels simultaneously and automatically flag anomalies that resemble the WOW signal. It serves as a constant reminder of the needle in a haystack nature of this cosmic search, where patience and persistence are paramount. The WOW signal stands as a singular beacon of possibility in the vast, quiet cosmos, a tantalizing, unresolved chord that continues to echo through the decades, challenging our assumptions, igniting our imagination, and reminding us that the universe is quite capable of holding onto its most profound secrets, even when it seems to have offered us a fleeting, tantalizing whisper. We have journeyed through the heart of our galaxy and the echoes of ancient signals, but now let's turn our focus to the final frontier of our own celestial backyard, a region so distant and faint that it exists more as a ghostly concept than an observed reality. This is the Oort cloud, a vast theoretical shell of icy planetesimals believed to envelop our entire solar system like a colossal spherical bubble. Imagine the farthest orbit of Neptune, the last of the recognized planets, and then keep going. Travel outward for another 1,000 times that distance until the sun is just a particularly bright star in a sea of blackness. You are now entering the domain of the Oort cloud, a reservoir of frozen remnants from the solar system's violent birth, a cosmic deep freeze holding trillions of icy objects in a tenuous gravitational embrace. This incredible structure is thought to operate in two main parts. The inner, more dense region, sometimes called the Hills cloud, blends into the scattered disk beyond Neptune. But the true extent of the Oort cloud lies much farther out, forming a spherical shell that begins roughly 2,000 astronomical units from the Sun and stretches outward to perhaps 100,000 astronomical units or more. To put that almost incomprehensible distance into perspective, a single astronomical unit is the average distance from Earth to the Sun. This means the outer edge of the Oort cloud could extend a quarter of the way to the next closest star, Proxima Centauri. At these staggering distances, the Sun's gravity is incredibly weak, and the objects within this cloud are only loosely bound to our solar system, easily swayed by the subtle gravitational tides of passing stars and the Milky Way itself. The primary evidence for this distant cloud's existence comes from the behavior of long-period comets. These are the spectacular, wandering visitors that grace our inner solar system on timescales of thousands or even millions of years. Unlike short-period comets, which originate from the Kuiper belt and have predictable orbits, long-period comets arrive from all directions in the sky, on highly elliptical paths that suggest a spherical source region. When astronomers trace the orbits of these comets backward, they find their aphelia the farthest points from the Sun cluster in that immense distant shell. The Oort cloud acts as a gravitational reservoir, occasionally nudging one of its icy inhabitants inward. A passing star's gravity, the tidal pull of the galactic plane, or a chance collision can dislodge one of these frozen worlds, sending it on a million-year fall toward the inner solar system, where the Sun's heat transforms it into the glowing, ethereal spectacle we recognize as a comet. This concept fundamentally reshapes our understanding of the solar system's boundaries. We often picture it ending at the orbit of Pluto or the edge of the Kuiper belt, but in truth, the Sun's gravitational influence, and by extension the solar system's domain, extends vastly farther. The Oort cloud represents the true outer limit, the final gravitational frontier where the Sun's pull is just barely strong enough to keep objects from drifting away into interstellar space. It's a borderland between solar and stellar dominion, a place where the orbits of icy bodies are so vast and slow that a single trip around the Sun could take many millions of years. This cloud is not a flat disk like the rest of the solar system. Its spherical shape is a fossil record of the solar system's formation, suggesting these objects were flung outward by the gravitational interactions with the giant planets in the chaotic early days, their orbits randomized over eons into the vast shell we infer today. The sheer scale and nature of the Oort cloud also present a profound challenge for observation and exploration. These objects do not generate their own light, and they are far too distant to reflect enough sunlight for our current telescopes to see directly. They are essentially dark matter of a solar system scale. Confirming its existence and mapping its structure is one of the next great frontiers in planetary science. Future telescopes with extraordinary sensitivity may one day glimpse the largest of these distant, dark icebergs, but for now, the Oort cloud remains a masterpiece of scientific deduction. It is a testament to our ability to infer the structure of the cosmos from the clues left by its messengers. The long-period comets that streak through our sky, each one a silent emissary from the frozen, unseen edge of our Sun's kingdom, reminding us that our home in space is far grander and more expansive than it appears. But sometimes the most profound mysteries are not found in the distant cosmos, but are revealed right here in our own solar system, etched into the precise trajectories of our robotic explorers. For decades, a subtle and persistent puzzle known as the Pioneer anomaly captivated and confounded physicists and engineers alike. It centered on the Pioneer 10 and Pioneer 11 spacecraft, two venerable probes launched in the early 1970s that were the first to travel through the asteroid belt and send back stunning close-up images of Jupiter and Saturn. After their primary missions were complete, these twin pioneers continued on their endless journeys into interstellar space, becoming humanity's first emissaries to the stars. But as they sped farther and farther from the Sun, navigators tracking their radio signals noticed something deeply strange. Both spacecraft were experiencing a tiny, constant, and unexplained deceleration back toward the Sun. It was as if an invisible hand was ever so gently applying the brakes, a force about 10 billion times weaker than the gravity we feel on Earth. But over the vast distances these probes traveled, this minuscule effect became impossible to ignore. The anomaly presented a classic scientific detective story. The first and most thrilling possibility was that this deceleration was the signature of new physics. Perhaps our understanding of gravity was incomplete on the scale of the solar system. Maybe Einstein's theory of general relativity needed a small modification, or there was an unknown form of matter or energy exerting a drag on the spacecraft. Some theorists even suggested it could be evidence for exotic ideas like the existence of extra dimensions, whose subtle influence would only become apparent far from the Sun. For a time, the Pioneer anomaly became a beacon for those searching for a crack in the foundation of modern physics, a potential revolution hiding in plain sight within the painstakingly collected data from our own backyard. Yet, the most likely explanation was always far more mundane, though devilishly difficult to prove. The leading hypothesis from the start was thermal radiation. Every object in space gives off heat, and the Pioneer probes were no exception. The electricity powering their instruments and systems inevitably produced waste heat. The spacecraft were designed with a main compartment called the bus that housed the vital electronics, and this compartment was heated by the radioactive decay of plutonium in their power sources. The theory went that this heat was radiating away from the spacecraft unevenly. While most of the heat escaped into space, a small portion was being reflected off the back of the spacecraft's large parabolic dish antenna. According to Newton's third law, every action has an equal and opposite reaction. If photons of heat were bouncing off the back of the antenna, they would impart a tiny push back toward the sun, creating the precise, steady deceleration that was being observed. It was a brilliant and elegant idea, but proving it required a level of detail about the spacecraft's thermal and geometrical properties that was incredibly challenging to reconstruct decades after their launch. The resolution of this decades-long mystery is a testament to the power of persistence and sophisticated detective work. A dedicated team of researchers, led by Slava Tarishev, undertook a Herculean effort to solve the case. They faced a monumental task, recovering old data stored on archaic formats like magnetic tapes and punch cards, tracking down original engineering documents and blueprints that were scattered and sometimes lost, and creating a complex digital model of the entire Pioneer spacecraft down to the smallest bolt and electrical component. This was not a simple simulation. It was a painstaking digital twin that accounted for how heat was generated by the onboard systems and how it flowed through the craft structure over its multi-decade mission. They modeled the power output of the radioactive thermoelectric generators as they slowly decayed, and they calculated exactly how much of that heat was radiated in every direction. After years of this meticulous work, the results were definitive. The digital model predicted a thermal recoil force that matched the observed anomalous deceleration with astonishing precision. The primary culprit was indeed the heat from the spacecraft's electronics and power systems. The asymmetry of the spacecraft's design was key. More heat was emitted from the back of the high-gain antenna than from the front, producing a net force that pushed back toward the sun. The anomaly wasn't a flaw in our understanding of the universe's fundamental laws. It was an unanticipated side effect of the spacecraft's own existence, a subtle photon pressure that had been overlooked in the initial mission planning. The case was closed not with a dramatic new discovery about gravity, but with a profound lesson in engineering humility, demonstrating that even the most carefully designed systems can harbor hidden, complex behaviors that only reveal themselves over time and across incredible distances. The legacy of the Pioneer anomaly, therefore, is not a revolution in fundamental physics, but something perhaps equally valuable, a masterclass in scientific rigor. It shows how a stubborn, tiny signal can drive decades of investigation and inspire bold new theories. It highlights the critical importance of archiving data and preserving engineering knowledge for future generations who may ask questions the original designers never anticipated. And it serves as a crucial reminder for all future deep space missions. Engineers designing probes like New Horizons, which flew past Pluto and is now exploring the Kuiper belt, now meticulously account for the tiny but cumulative effects of thermal recoil in their navigation models. What was once an unexplained anomaly is now a standard, calculated factor in plotting a spacecraft's course through the solar system. The story of the Pioneer anomaly is ultimately one of human curiosity and problem-solving, a puzzle born from our own technology that pushed us to look deeper, only to find that the answer was with us all along, hidden in the gentle, persistent push of light itself. And so we arrive at the final and perhaps most conceptually dizzying of our cosmic forces, a problem so fundamental it pits the two great pillars of modern physics against each other in a battle over the very nature of reality. This is the black hole information paradox, a puzzle that asks a seemingly simple question with profound implications. When something falls into a black hole, is the information that describes it lost forever? Our everyday intuition, and more importantly, a cornerstone of quantum mechanics, says that information must be preserved. You can burn a book, turning its pages to ash and smoke, but in principle, if you could collect every particle of soot and trace every photon of light emitted, you could theoretically reconstruct the book's entire content. The information is scrambled, but it is not destroyed. A black hole, however, presents a terrifying challenge to this principle. According to Einstein's general relativity, a black hole is defined only by its mass, electric charge, and spin. If you toss a grand piano, a collection of antique books, or a complex hard drive into a black hole, the black hole from the outside appears to remember only the total mass, charge, and angular momentum added. All the intricate details, the specific arrangement of atoms that made the piano a piano and the books books, seem to be utterly erased, swallowed by the singularity. This apparent violation of quantum mechanics' sacred rule of information conservation is the heart of the paradox. The plot thickened dramatically with Stephen Hawking's revolutionary discovery in the 1970s. He realized that black holes are not perfectly black. Due to weird quantum effects occurring just outside the event horizon, they slowly emit a faint glow of particles, now known as Hawking radiation. This radiation is thermal, meaning it is completely random and featureless, like the heat coming from a perfectly glowing coal. It carries away energy, causing the black hole to gradually lose mass and shrink over astronomical timescales until it eventually evaporates completely. And here lies the crux of the problem. If the only thing that comes out of a black hole during its long life is this random, information-less heat, then when the black hole finally vanishes, all the information about everything that ever fell into it vanishes with it. The universe would have a permanent case of cosmic amnesia, and the deterministic, predictable fabric of quantum mechanics would be torn apart. This information loss was so unsettling that Hawking himself famously bet against it, only to later change his mind as the debate evolved. For decades, physicists wrestled with this, and one of the most mind-bending proposed solutions is the holographic principle, which we touched on earlier. This idea suggests that all the information about what falls into a black hole is not stored in its mysterious interior, but is instead encoded on its two-dimensional event horizon, the surface of no return. Think of it like a cosmic scratchpad or the ultimate hard drive. Every particle that crosses the horizon leaves a tiny imprint, a kind of pixel, on this spherical surface. The information isn't lost, it's saved there in a vastly scrambled holographic form. Then, as the black hole emits Hawking radiation, this process isn't just random. The emerging particles are subtly influenced by the information encoded on the horizon, slowly and chaotically decoding the data and radiating it back out into the universe. By the time the black hole evaporates, the information has in principle been returned, albeit in a form so complex and mixed with the radiation from everything else that it is practically impossible to decipher. This solution preserves the sanctity of quantum mechanics, but requires us to accept that our three-dimensional reality might be a projection from a two-dimensional surface, a truly radical reimagining of space itself. Just when the holographic principle offered a potential path to peace, a new and even more violent paradox emerged from the depths of theoretical physics, the firewall paradox. Imagine you are an astronaut falling feet first into a very large black hole. According to Einstein's equivalence principle, the foundation of general relativity, you should feel nothing special as you cross the event horizon. It is a smooth, uneventful point in space. There is no there. Your journey toward the singularity would continue uninterrupted, at least for a while. This is known as the no-drama scenario. However, when physicists applied the holographic principle and strict quantum mechanics to this situation, they calculated something horrifying. For the information to be preserved and radiated back out via Hawking radiation, the entanglement relationships between particles just inside and just outside the horizon must be transferred in a very specific way. The mathematics suggested that this transfer would require a fundamental break in the vacuum of space, creating an immense wall of ultra-high-energy particles, a firewall right at the event horizon. Instead of a smooth crossing, our astronaut would be instantly incinerated into a plasma of fundamental particles the moment they reach the horizon. So, which is it? Does general relativity win, giving us a no-drama passage, or does quantum mechanics win, presenting us with a violent, paradoxical firewall? This dilemma forces physicists to confront the fact that our two most successful theories cannot both be completely correct in this extreme environment. The search for a resolution is driving some of the most exciting advances in theoretical physics, particularly in the quest for a theory of quantum gravity. Approaches like string theory and loop quantum gravity are attempting to describe the microscopic structure of spacetime itself, hoping to show what truly happens at the event horizon. In these frameworks, the concepts of a smooth horizon or a destructive firewall might both be crude approximations. The reality could be something entirely different and far stranger. For instance, some models suggest the event horizon is a fuzzy, quantum foam-like region, or that the interior of the black hole is somehow gravitationally repulsive, preventing a traditional singularity from forming. Others propose that black holes don't evaporate completely, but instead leave behind a tiny, stable remnant, a Planck-sized nugget that contains all the original information locked inside it forever. While this solves the information loss problem by never releasing the information back into the universe, it introduces its own puzzles about how an infinite amount of information could be stored in a finite, tiny object. Recent years have seen a fascinating shift in the debate, fueled by new mathematical tools and thought experiments. The concept of islands in the gravitational path integral approach has created a major stir. This complex formalism suggests that when calculating the evolution of a black hole, regions inside the event horizon, so-called islands, can actually contribute to the information carried by the Hawking radiation escaping from outside the horizon. It's as if the radiation we collect far from the black hole is somehow entangled with a part of its interior, a notion that seems to defy locality and our standard understanding of inside versus outside. This doesn't mean we can access the inside, but it provides a sophisticated mechanism for how information can escape without violating fundamental principles, all while potentially avoiding the need for a destructive firewall. It's a highly technical but promising development that shows how our thinking about this puzzle is continually evolving, blending quantum information theory with gravity in ways Einstein and his peers could never have imagined. Ultimately, the black hole information paradox is far more than an arcane argument among theoretical physicists. It is a profound probe into the fundamental laws of the universe, forcing us to question the nature of space, time, and information itself. The resolution, when it comes, will likely require a complete overhaul of our understanding, revealing a deeper truth where quantum mechanics and general relativity are seen as two different faces of a single, unified reality. It teaches us that even the most absolute darkness, the most perfect void of a black hole, may not be able to erase the story of what created it. In the grand cosmic ledger, every bit of information, from the spin of an electron to the memory of a star, appears to be permanent, woven inextricably into the fabric of the cosmos, ensuring that nothing, not even the universe's most voracious eaters, can truly make history disappear. From the ghostly tug of dark matter that sculpts galaxies to the relentless push of dark energy tearing the cosmos apart, our journey through 30 unseen cosmic forces reveals a universe humming with invisible activity. We've encountered the quantum fluctuations that wrote the blueprint for all cosmic structure in the first moments of time, and the Higgs field that gives substance to reality itself. We've felt the ripples of gravitational waves from colliding black holes and traced the silent shapeshifting of neutrinos from the heart of the Sun. We've explored the tangible pressure of the quantum vacuum in the Casimir effect and the vast, guiding influence of cosmic magnetic fields. We've even ventured into the speculative realms of tachyonic fields, the multiverse, and the holographic principle, where the very nature of space and time is called into question. Each force, from the enigmatic great attractor pulling our galactic neighborhood to the hypothetical actions that might constitute dark matter, plays a unique and vital role in the cosmic symphony. These are not separate curiosities, but interconnected threads in a single, magnificent tapestry, demonstrating that the reality we perceive is just the visible surface of a far deeper, more dynamic, and largely hidden existence. This exploration does more than just catalog cosmic oddities. It fundamentally reshapes our understanding of our place in the universe. We are not passive inhabitants of a static stage. We are active participants in a cosmos forged by these invisible architects. The very atoms in our bodies were created in the nuclear furnaces of long-dead stars scattered by supernova, and their existence relies on the precise tuning of fundamental forces. The fact that we can ponder these mysteries using mathematics, physics, and sheer curiosity to pull back the cosmic curtain is a testament to the profound connection between the universe and the consciousness it has spawned. The drive to understand these forces is what propels scientific inquiry forward, building ever larger colliders, launching more sensitive telescopes, and developing theories that stretch the limits of human imagination. Every answered question unveils new, deeper mysteries, from the black hole information paradox to the true nature of quantum gravity, ensuring that the adventure of discovery is far from over. As we stand at this frontier of knowledge, it's clear that the universe is far stranger, more vast, and more wonderfully bizarre than we ever could have imagined. The search for these unseen forces is ultimately a search for our own origins and our ultimate destiny, a story written in the language of mathematics and whispered through the phenomena of the cosmos. This conversation is just beginning, and your curiosity is a vital part of it, so we turn the question over to you now. Which of these 30 unseen forces captured your imagination the most? Was it the instant, spooky connection of quantum entanglement, the mind-bending possibility of the multiverse, or the silent, pervasive presence of dark matter? Let us know in the comments below. We read every single one. And if you're ready to continue exploring the furthest reaches of space, time, and mystery with us, make sure to subscribe and hit the notification bell so you never miss another journey into the unknown.